Hello, and I'm so glad you have stopped by Sleep Gravity. In this moment, let us quietly welcome a few more visitors as well. Some visitors come from very far away, yet they never knock on the door. They leave behind no sound. They do not change the color of the sky, and they do not make the ground beneath our feet tremble, not even slightly. They simply pass through, so silently that if humans did not have telescopes staying awake for us through the night, we might never know they had once crossed the light-filled region of the Sunday. For most of the time, the solar system seems like a familiar place. The sun sits at the center, the planets travel around it along long paths, comets from far away occasionally return, and asteroids continue their quiet motion through the old rocky region between Mars and Jupiter. All of this gives us the feeling that we live inside a system with order, with boundaries, with members that have already been recognized. But the universe is never truly closed in the way human beings may feel it is. Out there, between the stars, there are objects that no longer belong to any Sunday. They have left the place where they were born, or were thrown away a very long time ago, and then began a journey with no clear destination through the vast darkness. One of those objects passed through our neighborhood. It did not enter history through a brilliant image, but through a very small point of light in observational data. On the slopes of Haleakala in Hawaii, the telescopes of Pan-STARRS were quietly scanning the sky, just as they had done through many nights. They recorded faint points of light, compared their positions, and searched for tiny movements that the human eye could not recognize. Most of what appeared in the data belonged to things already familiar to astronomers. But in October 2017, there was one point of light moving in a way that did not quite resemble ordinary objects in the solar system. At first, it did not seem especially grand. It was too faint to become a spectacle in the sky. It did not trail a bright tail like the comets that once made people look upward. It also left no strong sign that would make the world immediately pay attention. But science sometimes begins with small things like this. A very slight difference. A path that does not match, a movement that makes people look again more carefully. And when astronomers looked more closely, the object began to feel difficult to understand. It was leaving very quickly. Its path did not look like a closed orbit around the Sunday. It seemed more like a visitor only passing through, having its path bent for a short time by the sun's gravity before continuing to move away from this place. By the time people realized how special it was, the best moment for observing it had already passed. It had gone beyond its closest point to the Sunday. It had swept through the brightest region of our star's light, and we could only watch it from behind, like finding the footprints of someone who had already crossed a sandy shore just as the tide was beginning to blur everything away. Later, that object was named Oumuamua. The name comes from Hawaiian, and is often understood as a messenger from far away arriving first. There is a gentleness in that name, but also a very deep mystery, because this messenger did not bring a clear letter. It did not tell us which star it came from, how long it had traveled through space, or what had pushed it away from its original home. It left behind only a few brief traces, weak light reflected from its surface, changes in brightness as it rotated, an open path through space, and a small motion not entirely produced by gravity. From those traces, a quiet question began to open. If an object from an unfamiliar star system only visits the solar system for a brief moment and then disappears, what can human beings learn from it? This question does not need to be told in a tense voice. It does not need to turn Oumuamua into something frightening, and it does not need to rush toward a mysterious explanation. Its fascination already lies within the natural truth itself. A piece of matter from the space between the stars passed through our region of the sky, and with that short appearance alone, it made the solar system suddenly feel wider in the human imagination. Before Oumuamua was discovered, scientists already had reasons to think that interstellar objects like this existed. When planetary systems form around young stars, countless pieces of rock, ice, and dust collide, change direction, are pulled by large planets, and sometimes are thrown out completely. A small fragment can lose its star and begin drifting through interstellar space. It no longer has seasons, no longer has days, no longer has a familiar orbit to return to. It simply keeps moving, carrying on its surface the traces of time, cosmic rays, and dark regions where human light has never touched. Perhaps Oumuamua was a fragment like that. Perhaps it once belonged to a distant planetary system, where there was another star, other orbits, and other objects we will never see. Or perhaps its true story is more complicated than anything we can guess from such a brief encounter. Science does not become weaker when it admits this. On the contrary, that honesty makes the story more beautiful. We know a few things, we can infer a few things, and a very large part of that object has already moved beyond our reach, together with the object itself. In this journey, we will follow the traces of Oumuamua at a slow pace. We will look back at how a faint point of light was found in the data, why its path showed that it was not an ordinary object of the solar system, and why its possibly strange shape made astronomers cautious. We will speak about the deep reddish color that may have been created by a long journey through space, about the unusual absence of a clear comet-like tail, and about the very small push beyond gravity that made Oumuamua one of the most unforgettable visitors in modern astronomy. But we will move through this story quietly. There is no need to turn it into a loud secret. There is no need to use fear to make it seem larger. Oumuamua is already special enough because it reminds us that the solar system is not a completely isolated island. Between the stars, there may be many silent paths where small pieces of matter still travel from one region of light to another. Some will never be seen. Some may pass by at a great distance, and very rarely, one of them steps into the range of human observation, close enough for us to realize that the universe has always held encounters with no warning. Perhaps in the future, new telescopes will discover interstellar visitors earlier. Perhaps humans will see them more clearly, measure their composition better, and maybe one day even send a small spacecraft to chase after an object that came from another star system. But with Oumuamua, that chance has already passed. It has been moving farther away day by day, returning to the dark space from which it once came, carrying most of its secrets with it. And perhaps that is enough for an opening. A visitor does not need to stay long to make a familiar place look different to those who live there. Oumuamua only passed through, but after it left, the sky no longer seemed as closed as before. From a faint point of light in the data, it left behind a feeling that is very gentle and also very deep, that out there, between the stars, there are still silent roads connecting strange, distant worlds with our small region of light. From that feeling, we can turn back to the very small moment when the story first began to be recognized by human beings. Not the moment Oumuamua entered the solar system, because at that time, no one on Earth knew it was coming, and not the moment it passed closest to the sun, because even then, it was still a nameless visitor in the darkness, with no name, no history, and no questions yet surrounding it. For us, the story began later. It began when the object had already passed through the nearest part of its journey, leaving humanity only a faint trace as it moved away. That trace did not appear in the sky as a brilliant spectacle. It was hidden in the data, on the summit of a volcano in Hawaii, where telescopes continued to stay awake through the night, in place of human eyes. On the summit of Haleakala, there are nights when the sky does not need to do anything special to feel deep. It only needs to open. Below, the island of Maui slowly sinks into darkness, with coastal roads, small rooftops, and distant lights fading like embers at the foot of the mountain. Above is a high, clear stretch of sky, where the air is thinner, drier, and starlight can pass through with less disturbance. At that altitude, human beings can no longer hear the rhythm of ordinary life as clearly. There is only the wind, the shadow of a sleeping volcano, and telescopes quietly doing the work that human eyes could never manage on their own. Pan-STARRS does not look at the sky in search of a beautiful story. It does not feel wonder before a bright star, nor does it linger over a distant cloud of dust like someone admiring a view. It observes with a different kind of patience, colder, steadier, and in its own way, more faithful. Night after night, it scans wide regions of the sky, records countless points of light, and lets processing systems compare every tiny change. A point of light that stays still may be a distant star. A point of light that shifts slightly may be a closer object, drifting through the solar system. The sky may seem motionless, but when it is recorded again and again, it begins to reveal movements that are very slow, very small, like a book that can only be read if we are patient enough to turn each page. There is a quiet beauty in the way modern astronomy works. Long ago, humans often told stories of the sky with the naked eye, through constellations and legends passed from one generation to another. Today, many great discoveries begin not with a sight that makes someone hold their breath, but with a very small difference between two images. A point of light is not exactly where it once was. A faint streak appears and then disappears. A change in brightness is so slight that, if printed on paper, it might not draw anyone's attention at all. Yet within that smallness, sometimes an entire story is waiting to be opened. In October 2017, amid the ordinary rhythm of Pan-STARRS observations, a faint point of light was recorded. It did not introduce itself. There was no strange glow around it. There was no clear shape that would immediately make people realize this was something never seen before. In the image, it was only a tiny dot among other tiny dots, so modest that if the story were told too quickly, a listener might think it was only a technical detail. But the sky often hides great things inside very small forms. A point of light like that, if it stays still, says nothing. But if it moves, if it leaves its old position in a way that is not entirely familiar, it begins to become a question. At first, that question was not loud at all. Astronomers were already used to the fact that the sky is always revealing small new objects. There are asteroids passing near Earth, faint comets moving inward from distant regions, dark pieces of rock that appear in images only when they happen to reflect enough sunlight. So a new point of light does not immediately become a major discovery. It has to be checked. Older images have to be reviewed. Its position has to be measured. People have to ask whether it might be an imaging error. They have to try to build a temporary path from the few scattered markers available. In its earliest moments, science often does not sound like a cheer of excitement. It is more like a very careful hand resting on a sheet of paper, afraid that if it moves too quickly, it might blur the thin line of ink that has only just appeared. The strange thing about that point of light was not in its appearance. It was not beautiful in the usual sense. It was not large, not close, not bright enough to become an object that millions of people could look up at and point to together. The strangeness was in the way it moved. When the observed positions were connected, its path began to feel unlike the familiar ones. An object in the solar system can travel very far. It can take tens, hundreds, or even thousands of years to return, but it is still usually held by the sun with an invisible cord of gravity. It moves away and then comes back, like a grain of dust traveling along a long arc around a central lamp. But this point of light did not seem to enter the story that way. It felt as though it had passed through, rather than coming back. The sun did pull on it, did bend its path, but did not turn it into a member that would remain. This was the feeling the numbers began to whisper. Not the whisper of mystery, but the whisper of geometry and motion. An object entered the inner solar system at high speed, swept through under the pull of the sun's gravity, and then continued carving its way outward. Not a loop, not a seasonal return, only a very brief visit within a journey longer than anything human beings could follow. But in the beginning, none of this was stated so clearly. A discovery is not born complete in the moment it is seen. It grows through checking, through additional observations, through calculations done again, through data searched for in archives. There is something deeply human in that process. In a universe too vast, we do not have the right to demand that truth appear whole before us all at once. We can only pick up each small sign, place them beside one another, correct mistakes when needed, and patiently wait for the picture to become a little less blurred. So before the name Oumuamua appeared, before it became the first confirmed interstellar object to pass through the solar system, before debates about its shape, composition, and strange motion spread across the scientific world, it was only something very simple, a point of light that needed to be checked further. Perhaps it is exactly that simplicity that makes the story more beautiful. A visitor from very far away does not have to appear like a door suddenly thrown open. Sometimes, it enters human awareness as a tiny dot in an image, so quiet that only the most patient observing systems can realize it was ever there. Think of the small amount of light that created that point. Light from the sun traveled outward, touched the dark and cold surface of the object, and then a very small portion of it returned to space, crossing an immense distance before falling into the mirror of a telescope on Earth. From that little bit of light, humans began to ask, where is this object? Where is it going? Where has it been? And does it belong to the familiar paths around the sun? A little light, if listened to in the right way, can become a message from very far away, not a message written in words, but in position, speed, brightness, and tiny changes over time. Astronomy is often the art of trusting fragile things. We know the composition of stars through thin dark lines in their spectra. We know there are planets around distant stars through slight dimmings of light that are almost too small to notice. We know the universe is expanding because light has been stretched across distances we cannot fully imagine. And here, human beings began to know an interstellar visitor through a faint dot moving across a few survey images. The greatest things do not always arrive with great signals. Often, the universe only places before us a trace just large enough and leaves the rest to patience. On Haleakala, that night was probably not very different from the nights before it. The wind still moved across the mountain slopes. The ocean still lay dark and wide below. The machines still followed their schedules. No one could have sensed by intuition that a new boundary in human understanding was being touched. Because when a discovery is still inside the data, it does not yet have the shape of history. It does not yet have a beautiful name, or headlines in newspapers, or great questions gathered around it. It is only a small sign waiting to be understood correctly. But from that small sign, everything began to shift. A point of light was found. A path was built. An unusual pattern slowly appeared. And with it, the solar system no longer looked only like a closed system filled with familiar objects traveling around the Sunday. At the edge of human awareness, something from outside was lightly touching our story. Not with sound, not with brilliant light, but with a small movement in the data. That is why the beginning of this story does not need to start with great astonishment. It begins with attention. A kind of attention that is quiet, steady, and deeply human. We cannot see everything that passes through our region of the sky, but we have learned to place telescopes on high mountaintops so they can stay awake through the night for us. We have learned to preserve light inside data files, to compare tiny points, to notice when something no longer sits where it used to be. And because of that, an object that had almost passed through in silence was still able to leave a trace. That trace did not yet explain what it was. It did not say where its home was. It did not reveal whether it was made of rock, ice, dust, or some unusual mixture of all of them. But it had done the first thing every scientific story must do. It made human beings look more closely. From here, the question was no longer whether there was a point of light in the data. The question began to become something deeper. Why did the path of that point of light not resemble the objects we had known before? And as that path opened, Oumuamua began to step out of the darkness of a small discovery, becoming the first visitor from between the stars that human beings had ever recognized in time. When a new object is found in the sky, the first thing humans usually want to know is very simple. Where is it now, and where will it go next? But with Oumuamua, that question carried a slightly different feeling from the very beginning. Because when the first calculations began linking its positions together, astronomers realized that the most important part of the encounter was no longer ahead of us. It had already happened. The object had passed its closest point to the sun before humans had time to understand what it was. The strongest light, the most favorable distance, the most precious time to see it a little more clearly, all of it had passed by in silence. Some discoveries make people feel as though they are opening a door at just the right moment. But other discoveries feel more like stepping into a room after the guest has already left, with only a slightly shifted chair, a faint trace of dust on the floor, and the sense that something important happened not long ago. Oumuamua belongs to the second kind. When it appeared in the data, it was no longer moving toward the center of the story. It had already swept through the inner region of the solar system, had passed closer to the sun than Earth, had received the warmth and gravity of our star, and had begun to move away. Humans did not see it when it arrived. We only managed to see it as it was leaving. That lateness gives the whole story a strange rhythm. In astronomy, many objects can be observed for years, even for centuries. A planet will appear again in the sky. A periodic comet may disappear and then return decades later. An asteroid continues moving around the sun, giving humans more chances to measure it, correct earlier estimates, and understand it more clearly. But with Oumuamua, the opportunity narrowed day by day. It was not following a loop that promised a return date. It did not belong to a familiar orbit that astronomers could wait for and observe again next season. It was leaving the bright region of the sun, and the farther it went, the fainter, smaller, and harder to capture it became in images. A dark object in space does not shine by itself. It can only be seen when sunlight touches it and reflects back toward us. That sounds simple, but it makes timing extremely important. When the object is closer to the sun and closer to Earth, the reflected light may be strong enough for telescopes to record more details. When it moves away, that amount of light drops quickly. It is like a small boat leaving the dock at night. If we see it while it is still nearby, we may recognize its shape, its direction, sometimes even the color painted on its hull. But if we only notice it after it has already gone far away, what remains is only a small point on the dark water, and then that point slowly blends into the night. With Oumuamua, astronomers had to work within that very fading. Every new observation was precious, but every observation was also harder than the one before. Large telescopes on Earth were aimed toward it. Its positions were measured again. Its brightness was monitored. People tried to find older images in the data from before the discovery, as if searching through the sky's diary to see when this visitor had passed by without anyone noticing. This was a very particular kind of tracking, not following the trail of an object approaching us, but following the trail of an object escaping from view. What made that tracking feel tense, yet still quiet, was that time was not on humanity's side. In many scientific stories, we can say observe more as if it were a natural solution. But here, observing more was not always easy. Oumuamua was moving farther away. It did not wait for telescopes to have open schedules. It did not wait for research teams to agree on what to call it. It did not wait for humans to finish debating whether it was an asteroid, a comet, or some other kind of object. It simply continued along its own path, as though being discovered or not had nothing to do with a journey that had begun long before. Perhaps that is why this story can touch a very human feeling. In life, we also sometimes understand something important only after the best moment to ask more has already passed. Someone leaves, and only then do we realize there are still so many things we do not know. A door closes, and only then do we notice the trace left on the handle. A train has already pulled out of the station, and only then do we see a small piece of paper left behind on the platform. Science often tries to stand outside comparisons like this, but the listener does not. We understand the regret of data that arrives late. We understand the feeling of having to learn so much from so little that remains. And yet, That lateness did not make the discovery less valuable. On the contrary, it gave each piece of data more weight. When there could be no close-up photograph, people had to listen to the brightness. When they could not touch the surface, they had to read the color. When they could not fly after the object, they had to reconstruct its path with mathematics. Each small number became like a fragment of pottery found from a civilization that had already moved far away. It cannot tell the whole story, but if placed correctly, it can reveal the shape of something larger. Astronomers began looking into the object's recent past. How had it passed through the inner solar system? How had it approached the sun? How much had the sun's gravity bent its path? And before it entered our region of light, from what direction in the sky had it come? Each question was like a step backward along the road Oumuamua had just left behind. It could not be brought back to where it had been. It could not be made to stop. But the remaining measurement points could be used to draw a curve, and from that curve, people could understand that this was not ordinary motion. Its closest point to the sun became a special marker in the story. That was where the object received more heat, where its surface might have reacted more strongly if it contained volatile materials, where an ordinary comet might have begun to reveal gas and dust more clearly. But at that moment, we did not yet know it was worth such attention. There was no large observing campaign prepared at the right time. No spacecraft was waiting along its path. No scene of human beings looking up together and seeing a strange visitor brighten in the sky. That moment passed almost unwitnessed, and only afterward, through late arriving data, did humans understand what they had missed. But saying we missed it is only half true, because without pan-stars, without sky survey systems working steadily, we might have missed everything. Not just the best moment, but the event itself. Oumuamua could have passed through the solar system, continued outward, and never had a name in any human scientific story. It would still have been itself, still traveling on its own path, but we would not have known. So within that regret, there is still something very beautiful. Even though it was late, humanity still recognized it in time. Even if all we could do was look after it as it left, that look was enough to open a new kind of question. As the observations were gathered, this object was no longer simply a nameless point of light. It began to have a short history within our data. One position before, one position after. A brightness that changed over time, a direction of departure. A sign that it had passed the sun and was not coming back. The data was not abundant, but it was enough to do the first and most important thing: separate it from the familiar. It was not only a newly discovered small object, it was a small object discovered as it was moving away from us, after a brief visit that would probably never repeat within a human lifetime. The more we think about it, the more Oumuamua feels like a story told from the ending. We knew it was moving away before we understood where it had come from. We watched it grow fainter before we knew its true shape. We gave it a name after it had already passed through the most important part of its journey near the Sunday. That order is not the way human beings usually want to understand the world. We like to begin with an origin, follow the events as they unfold, and then arrive at a conclusion. But the universe does not always tell its stories in an order that is convenient for us. Sometimes, it leaves only the final part behind, and from that ending, humans have to quietly work their way backward. There is something gentle in that act of going backward. It is not a loud pursuit. It is more like following the light of a lamp that went out long ago, with only a trace of it, still lingering on the wall for a moment. Astronomers knew that with each passing night, Oumuamua would become harder to see. But for that very reason, the final observations had to be preserved with care. Not to possess it, not to solve everything at once, but so that after it had disappeared completely from view, humans would still have enough data to ask the next questions properly. And that next question was not only when it had passed through. More deeply, the question was this: what did its path say about where it belonged? If an object travels around the sun, we can see it as part of this gravitational family. If it only passes through and leaves, then we have to widen the story beyond the familiar boundary. So how did Oumuamua arrive, with what speed, and from what direction? Why did the sun only bend its path without holding it? And how did astronomers know that this was not a very distant comet returning, but a visitor that had come from the space between the stars? At the end of that late tracking effort, a new feeling began to appear. It was no longer only the regret of discovering it late. It was no longer only curiosity about a faint point of light. It was the feeling that the path of this object was saying something deeper than its shape, deeper than its color, even deeper than the name humans would give it. That path was like Oumuamua's first signature. And when astronomers began to read that signature, they realized that this visitor was not traveling along the old roads of the solar system. The path of an object in space is sometimes like a very brief introduction. It does not tell us what the object is made of. It does not describe whether its surface is cold or hot, old or new, smooth or rough. But it can reveal something more important than appearance, whether that object belongs to this region of space or is only passing through. With Oumuamua, before humans understood its true shape, before debates began about its color, composition, and unusual motion, its orbit was what first made astronomers look more closely. A small point of light may not seem impressive in an image, but when that point of light leaves behind a path that does not close around the sun, the story immediately becomes different. The solar system is not held together by a wall, but by gravity. The sun lies at the center with an enormous mass, and that mass pulls on everything around it with an invisible force. Earth does not fly straight into the darkness because it is falling around the sun along a stable orbit. Jupiter, Saturn, the asteroids, and distant comets are all held in different ways by that same pull. Each object has its own distance, speed, and tilt, but they all share one thing in common. Their paths are held by the sun inside a long story. Some paths are nearly circular, steady, and easy to predict. Others are far longer, carrying an object so far away that it disappears from view for decades, centuries, and then later returns near the sunday. A comet can make human beings wait a very long time, but if it remains bound, it still has the possibility of coming back. It is like someone leaving home to travel through many lands, perhaps taking many years to return, yet still carrying a thin thread that connects them to where they began. For objects that belong to the solar system, that thread is the gravity of the sunday. Oumuamua did not move with that feeling. When the observed positions were placed beside one another, its path did not form a loop that would return. It entered the inner solar system, was pulled off course by the sun, and then continued moving away. The sun was not powerless. Its gravity still bent the object's motion, much like a deep valley can change the direction of a rolling stone. But if the stone is moving too quickly, the valley cannot keep it there. It only passes through, changes direction, and continues rushing out the other side. With Oumuamua, astronomers saw a curve like that, the influence of the sun, but no return. In astronomy, this kind of path is called a hyperbolic orbit, or more simply, an open orbit. We do not need to hold on to the term as if it were a heavy formula. It is enough to remember that a closed orbit is the path of an object that is still being held, while an open orbit is the path of an object that comes from outside and then leaves that region of gravity. A planet traveling around the sun follows a closed orbit. Many periodic comets do as well, even though their loops are much longer and more stretched out. Oumuamua was more like a guest stepping into the light before the front porch, passing by, and then continuing on its way into the night. Speed is the part that makes the story clearer. If an object approaches the sun while moving slowly enough, the sun's gravity may be able to hold it or pull it into a very long orbit. But if it already carries too much speed, the sun can only change its direction, not turn it into a new member of the solar system. This is like the difference between a leaf falling onto still water and an arrow slicing through the air. The leaf may be caught by a current. The arrow, if it is moving fast enough, only shifts its direction slightly and keeps flying. Oumuamua passed through our region with a speed that made its path unlike a return trip from the distant edge of the solar system. What is beautiful here is that human beings did not need to see the entire journey with their own eyes to understand that important part. We were not standing outside the solar system, looking at Oumuamua's orbit as a bright line drawn against the black. Earth itself is moving. Telescopes are also looking from a viewpoint that is traveling around the Sunday. So astronomers had to separate many layers of motion from one another. The motion of Earth itself, the apparent position of the object in the sky, the pull of the sun, and even smaller influences from the large planets. From a few brief measurement points, they reconstructed a path through three-dimensional space. And when that path became clearer, it did not resemble the familiar roads of objects born around the Sunday. We might imagine it as seeing a few footprints on a dusty road. If there is only one footprint, we do not know much. If there are several footprints following one another, we begin to understand which way the person was walking, whether they were moving slowly or quickly, whether they turned back or not. Oumuamua left very few footprints like that, but those footprints were accurate enough to show that it was not moving in a loop. It was not making an appointment to return. It was not a periodic comet appearing after a long journey. It had entered the solar system from one direction, swept through under the influence of the sun, and then opened its way out of this system. At that moment, the idea of an interstellar object became more concrete. It was no longer only an idea in a scientific model, and no longer only a possibility that had been predicted for a long time. It became a real object, with measured positions, recorded brightness, and a path clear enough for humans to know that it had come from the space between the stars. The word interstellar does not simply mean very far away. It means that the object does not belong to the long-term orbits around the Sunday. Before it entered our field of observation, it had been part of the vast space that lies between star systems. But knowing that it came from outside does not mean knowing exactly where it came from. This is a point that should be kept gentle, but clear. We can recognize that someone does not live in our village if we see them passing along the main road and then leaving. But that does not tell us which village they were born in, how long they have been traveling, or why they left home. It is the same with Oumuamua. Its open orbit shows that it was not held by the sun, but it is not enough to trace it with certainty back to a parent star. The stars in the Milky Way are also moving. The sun is moving as well. Oumuamua itself may have been drifting through space for a very long time. Even a tiny uncertainty in speed or direction, when carried backward over millions of years, can make the starting point blur. That blurriness does not make the discovery less meaningful. It only reminds us that a brief encounter always has limits. We know the path of the visitor as it crossed our region of light, but the earlier part of its journey remains held by the dark. Science here does not play the role of a storyteller who knows everything. It is more like someone who finds a few scraps from a letter that has been carried away by the wind. Those scraps contain real writing, real information, and enough meaning to piece together part of the message. But no one should pretend to be holding the whole letter. So, the most memorable thing here is not an orbital term. What matters is the way a path can expand the human feeling of the solar system. Before Oumuamua, we might have thought of the region around the sun as a system with familiar members: planets, moons, asteroids, comets, dust, and ice. After its path was understood more clearly, that picture gained a passageway running through it. The solar system no longer seemed like a house with its doors absolutely closed. It felt more like a region of light along a very long road, where, from time to time, an object from a strange distant darkness passes by. This does not need to be told with drama. An interstellar object passed through without causing any disaster, without colliding with any planet, without changing the order of the familiar orbits. It simply passed through. But that very calmness is what gives the story depth. The universe does not always widen human understanding through brilliant explosions or enormous images. Sometimes, It sends only a faint dot, and inside that faint dot is a path that will not return. Once the path had said that Oumuamua was an interstellar visitor, astronomers began listening to other signs. If its orbit told us that it did not belong here, what else could the reflected light from its surface reveal? An object too far away to photograph clearly can still reveal its shape through the way it brightens and dims. If it is rotating in space, the amount of light reflected back toward Earth will change as different sides turn into view. From those very small fluctuations, humans may not be able to see its body directly, but they can still infer that it may not be round, not even, and perhaps much more unusually shaped than it first seemed. The path was the first sign. Light would be the next, and when the light of Oumuamua was followed more carefully, this interstellar visitor was no longer strange only because of where it came from. It began to seem strange even in the way it rotated, the way it reflected the sun, and the way a dot too small and too faint in the sky could lead humans to imagine a shape unlike the familiar objects we had known before. Before going deeper into the light of Oumuamua, perhaps we should pause for a moment with its name itself. In science, names are often very short, sometimes dry, sometimes only numbers and symbols meant to distinguish one object from another. But from time to time, a name manages to hold a small part of the feeling from the moment of discovery. It does not make the object artificially more mysterious, and it does not replace data with poetry. It simply helps humans remember that behind the measurements, behind the orbit and the brightness, there was still a very strange encounter between our curiosity and a piece of matter that had traveled through the darkness between the stars. Oumuamua is such a name. It comes from Hawaiian and is often understood as a messenger from far away arriving first. That way of calling it alone softens the story. If it had always been known only by a string of numbers or a cold identifying code, we could still study it, still calculate its path, still write scientific papers about it. But perhaps the feeling of the encounter would be different. A name does not change the nature of an object, but it does change the way humans step into the story. It places before us not a threat, not a mystery that needs to be exaggerated, but a quiet visitor that brought a sign from a very distant place. That name also fits the circumstances of the discovery. Oumuamua did not arrive like a messenger placing a clear letter directly into our hands. It did not leave behind a map pointing back to its home. It did not tell us which star system it once belonged to, how long it had drifted through space, or give humans enough time to look more closely. It simply passed through, then moved away. So if we call it a messenger, it is a very silent one. Its message does not lie in words, but in motion. Not in a complete answer, but in the questions it forced human beings to ask. There is something very beautiful in the fact that an object from interstellar space was named in the language of the place that saw it. Pan-STARRS sits on Haleakala, beneath the skies of Hawaii, where the first observations brought the object into human awareness. From a faint dot in the data, it received a name connected to the land below the telescope. Not because the object belongs to Hawaii, and not because humans can possess it by naming it. On the contrary, the name reminds us that every cosmic discovery has two sides. One side is space itself, too vast for us to easily imagine, where the object crossed distances beyond our understanding. The other side is a very specific point on Earth, a mountaintop, a telescope system, and human beings reading data within the limits of their own lives. When we hear the phrase, "a messenger from far away," it is easy to ask at once, what message did it bring? But with Oumuamua, that question should not be answered too quickly. Perhaps its first message was simply its own existence. Before it passed through, scientists had predicted that interstellar objects must exist. That made sense, because planetary systems can throw out countless fragments of rock and ice during the process of formation. But a prediction is still different from a real encounter. Oumuamua was like a small piece of evidence drifting into our field of observation, enough to turn a long-standing possibility into a specific event. It said, in a very quiet way, that the space between stars is not only an empty region for light to pass through, Small objects are wandering there as well. Another message lies in the limits of the encounter itself. Oumuamua teaches humans that not every object worth noticing will stay long enough for us to understand it completely. Some cosmic phenomena move so slowly that humans have generations to observe them. There are variable stars, orbiting planets, and distant galaxies that can be seen again and again. But there are also things that appear only within a very narrow window of time. If we discover them late, the data will be limited. If we do not have sensitive enough telescopes, the object will disappear. If we want a complete answer, the universe may not give us enough time. So the name Oumuamua does not only suggest a messenger arriving from far away, it also carries the feeling of a messenger who has already stepped through the doorway before we have had time to prepare a chair and listen. That makes the story humbler. We can measure its path, but we cannot know its home with certainty. We can follow the changes in its brightness, but we cannot see its true shape with our own eyes. We can build hypotheses about its composition, but we cannot hold a piece of its material in a laboratory. In many popular science stories, people often want every mystery to end with a strong, neat, final answer. But Oumuamua does not allow that kind of easy certainty. It left just enough data for science to enter, but not enough for curiosity to become self-satisfied. And perhaps this is also why the name has more lasting life than a code number. A code number helps us store information. A name helps humans remember the feeling of the encounter. When we say Oumuamua, we are not only speaking about a small object that passed through the solar system in 2017. We are also speaking about the first time humanity confirmed an interstellar visitor in our own region of sky. We are speaking about the moment the solar system, which we had long imagined as its own separate system, suddenly seemed to have an opening. We are speaking about how an object that did not belong to the sun's family could still enter its region of light, pass through quietly, and disappear toward dark spaces we cannot yet follow. The name also helps keep this story from being pulled too far toward fear. When a strange object arrives from beyond the solar system, the human imagination can easily run faster than the data. We may want to turn it into a mysterious sign, a secret message, an artificial object, or something beyond science. But the name messenger from far away can be understood in a gentler way. A messenger does not necessarily have to carry an intention. In the universe, many things bring messages simply by existing. A grain of dust inside a meteorite can bring a message from the early solar system. Light from a distant galaxy can bring a message from the cosmic past. A spectral line can bring a message about the elements inside a star. Oumuamua is the same. It does not need intention in order to carry information. Its existence, its path, and its faint light were already a form of information. In a slow narration, the name Oumuamua feels like a pause between two layers of understanding. Before this, we followed the data and the path to understand why this object was unlike the familiar members around the Sunday. After pausing with its name, we will begin to look at its light. But before moving on, it is worth keeping the feeling that science is not only classification and measurement. Science is also a way humans learn to pay attention. A faint point of light was noticed. A strange path was noticed. A name was given not to bring the object physically closer, but to help human memory hold on to that encounter. Perhaps in the future, many other interstellar objects will be discovered. Some may be seen earlier, some may be brighter, with clearer tales, or may give us far more data. By then, Oumuamua may no longer be the only interstellar object in scientific memory, but it will still hold the special place of the one that came first. Not because it explained everything, but because it opened the first door. Later visitors may leave clearer stories behind, but the first visitor always changes the way we look at the doorway. Within that name, then, there is a very gentle mixture of science and humanity. Science needs paths, speed, brightness, measurements, and uncertainties. Human beings need a way to call the thing that has just touched their imagination. Oumuamua rests between those two needs. It is a real object, truly observed, passing through the solar system along a real path. But it is also a small symbol of the feeling that the sky does not stand still around us. Some things come from very far away, pass through very quickly, and if we are fortunate, we have only enough time to give them a name before they fade from view. The more we think about that name, the more we see that it does not close the story. It simply makes the story easier to listen to. A messenger from far away arrived first, but its message is not contained entirely within the name. That message is scattered through the remaining pieces of data: the changing brightness, the color of the surface, the absence of a clear comet-like tail, and a small motion that would continue to make scientists think for a very long time. The name helps us call it, but the light is where we begin to read further. So after understanding why Oumuamua's path did not resemble an object belonging to the solar system, we can turn toward a more subtle sign. No longer the road it traveled, but the way it appeared through the telescope. A point of light too far away to give us a close-up image can still brighten and dim with the rhythm of its own rotation. In that faint change, astronomers began to realize that this messenger from far away did not only have a strange journey. Its silhouette, though never clearly seen, may also have been unusual enough to deepen the entire story. After the name, what remains for humans to read is not a clear image. Oumuamua does not appear in telescopes as a small world with a visible surface. There are no rock slopes, no impact craters, no sharp edges for the eye to grasp. In observational images, it is only a faint point of light, so small it almost blends into the dark background. Yet that point of light does not keep a constant brightness. It rises and falls, dims and brightens, as if an object is rotating somewhere in the darkness, occasionally tilting a different face toward the Sunday. Sunlight travels outward, strikes the surface of Oumuamua, and then a very small portion returns to Earth. That small portion of light is all the telescope can capture. If the object were stationary and fairly uniform in shape, its brightness would likely change less. But as astronomers tracked it over multiple observations, the light did not follow a steady, flat path. It fluctuated noticeably. At times, the faint dot brightened. At other times, it dimmed significantly. Within that rise and fall, the first shadow of Oumuamua began to emerge not as a drawing, but through the rhythm of reflected light. A rotating object can reveal its shape in a very subtle way. If its wider side turns toward us, more light is reflected back. If a narrower side faces the telescope, the light diminishes. Objects that are nearly round may brighten and dim slightly, because their surfaces are not perfectly uniform, but the changes are usually small. With Oumuamua, the variations were large enough that people began to consider an elongated, flattened, or otherwise irregular shape, rather than a simple rounded rock. Yet no one ever actually saw its body. There are no close-up images to confirm whether it was long like a piece of wood, thin like a shard, or distorted in some other way. The famous illustrations of Oumuamua, though memorable, are still human reconstructions from data. At times, it is depicted as a long, dark object, resembling a cigar drifting through space. Other models suggest it may be flatter, like a wide, thin fragment of matter. Both visualizations come from the same fact. Its brightness changed too much as it rotated. So the most certain thing is not a particular illustration. What is more certain is that Oumuamua did not behave like a roughly spherical object reflecting light evenly. It seems to have a shape that caused its reflective area to vary significantly over time. An object like that, if rotating in space, will flicker with its own rhythm, not flickering because it emits light, but because each rotation presents the sun and our telescopes with a different face. One can imagine a dark piece of rock quietly spinning in space. When its broad side faces outward, it catches more light. When its narrow edge tilts away, it almost disappears into shadow. The rotation continues, the light rises again, then dims. No sound accompanies this motion. No signal is strong enough for the human eye to perceive. Only the numbers quietly record an object spinning, moving away, and revealing part of its form through the small amount of light it can send back to Earth. Astronomers call that kind of data a light curve, but the technical name aside, it is really quite simple. The brightness of the object measured over time. Each measurement is a moment. Connecting many moments together does not give a portrait, but it provides a rhythm. That rhythm tells us the object is not still. It is rotating. And in that rotation it reflects light unevenly. Within that unevenness, its shape begins to become a real question. Small objects in space do not need to be round. Large planets have enough gravity to pull their matter into roughly spherical shapes. A smaller object is different. It may retain a distorted shape from ancient collisions. It may be a fragment of a larger body. It may have been stretched, bent, impacted, or formed in a chaotic environment long ago. Weak gravity is not enough to make it tidy. So an irregular shape for an asteroid or comet is not surprising. But with Oumuamua, the unusual aspect lies in the degree of brightness variation and its interstellar origin. A small irregular object is already interesting. A small irregular object from beyond the solar system makes each clue carry even more weight. If it once belonged to a distant planetary system, its current shape may be the trace of a history humans did not witness. Perhaps it is a fragment from a collision. Perhaps it was once part of a young cluster of material around another star. Perhaps a large planet altered its path, ejecting it from its parent system, sending it drifting through interstellar space for a long time. Those possibilities cannot yet be narrowed to a single answer. But Oumuamua's fluctuating light makes all those possibilities feel more alive. It is no longer just an anonymous dot of light. It begins to resemble an object with a body, a motion, a past, even though all remain obscured by distance. The absence of close-up images also makes every inference fragile and precious. If a spacecraft had flown past it, the story could have been different. We could have seen the real outline, the real surface, the true light, and dark patches. We could know whether it was long or flat, smooth or rugged, dusty or cracked. But there was no such near encounter. Oumuamua passed too quickly, was discovered too late, and then moved away just as humans began to realize it was noteworthy. What remains are its trajectory, brightness, color, and measurements to be treasured like shards of glass left after an object has slipped from reach. During that brief interval, its light still accomplished something important. It broke the simple assumption that an interstellar visitor might be just an ordinary small rock passing through. Perhaps it was not so ordinary. Perhaps it carried an elongated body, a flattened form, or a distorted structure, causing each rotation to change its brightness. It did not need to be mysterious to be memorable. Its irregularity was enough. An object from the darkness between stars, rotating in silence, sending a faint pulse of light back to Earth, left astronomers with the question, what shape could produce such a light curve? That question is not rushed. It requires models, assumptions, and different methods of testing. If a shape is proposed, it must explain the measured brightness. If a rotation pattern is proposed, it must match the rhythm of change in the data. If multiple explanations remain possible, science accepts holding them alongside each other rather than selecting the most visually appealing. Oumuamua thus does not become a sculpted statue. It resembles a shadow built from light, always with slightly blurred edges, always retaining a portion that cannot yet be confirmed. Even so, a faint shadow can still change the way we perceive it. Before looking at its light, Oumuamua was an open path, a visitor that would not return. After monitoring its brightness, it gained an imagined body constrained by the data. A body spinning, irregular, perhaps elongated or flattened, unlike a peaceful round rock. That object began to have form, even if that form was never fully revealed to the eye. Perhaps it is this half-seen, half-hidden quality that makes Oumuamua so unforgettable. It does not give too little to be ignored, but it also does not give enough to be fully understood. It leaves a trajectory clear enough to declare it does not belong here. It leaves a brightness rhythm strong enough to suggest that its shape is unusual. And then it continues moving away, as if each clue were released just enough before the darkness closed behind it. That light has yet to tell the full story. Beyond its rising and falling with rotation, it carries a color. Oumuamua appears reddish, not the bright red of fire, but the dark red of matter that has long endured the space environment. Such a color may speak of a surface weathered by time, radiation, and cosmic rays over immense distances. After shape, color reveals another layer of this interstellar visitor. Not how it looks at a single moment, but what its surface may have experienced before passing through the sun's light. After the rhythm of brightness hinted at Oumuamua's unusual shape, its color takes the story a layer deeper. It is no longer just about whether the object is long or flat, spinning fast or slow, reflecting more or less light, but about what that tiny surface has experienced before being illuminated by the sun in this fleeting moment. In the observational data, Oumuamua does not appear in a vivid or easily described color. It is not fiery red, not metallic bright, and not the pristine hue of newly exposed ice. Its tone leans toward deep, subdued red, dark and muted, like matter that has been touched by space for a long time. Long enough that time leaves no obvious cracks, only a quiet layer covering the surface. An object drifting through the universe does not need rain, wind, or oceans to be altered by time. On Earth, rocks are worn by water, air, temperature, plant roots, and the passing seasons. In space, the process is quieter, but not lighter in any deep sense. A fragment of rock or ice wandering between stars may be bombarded by cosmic rays over long periods, pierced by high-energy particles through its outer layers, altered by ultraviolet light from distant stars, and occasionally brushed by interstellar dust in impacts too small to create a spectacle, but persistent enough to contribute to the history of its surface. There is no sound in those encounters, no seasonal change, only subtle effects accumulating over spans too long for human memory to hold. That deep red, then, is not a layer of paint applied from outside, but a natural surface built by its journey. If Oumuamua once had a younger, brighter, or less altered surface, the long time in space may have darkened and reddened the outer layer. On many icy bodies in the distant solar system, astronomers have also observed similar red or reddish-brown hues, often associated with carbon compounds altered by radiation over time. Oumuamua does not have to be identical to those objects, but its color evokes a surface aged in the way of the cosmos. Not aged from dust in a room, but aged from exposure to radiation, cold darkness, and immense distances. There is a sense of solitude in that color. A body wandering between stars has no familiar sunrise, no sun regularly pouring light over its surface, no warm or cold seasons as a planet with a stable orbit might experience. It passes through regions where starlight is sparse, where a star is only a distant white dot, and through stretches where darkness dominates, interstellar dust is thin, and high-energy particles silently streak across space. In such a journey, red is not just a color. It is the trace of prolonged exposure, a very thin memory left by space upon matter. As Oumuamua passed through the sun's light, the starlight struck its surface and reflected a tiny portion back toward Earth. That faint light carried hints of its color, but it did not tell a clear story immediately. It only indicated that the object was not overly white, not blue, not like freshly exposed ice under sunlight. It appeared darker and redder, closer to the feeling of a surface aged by space. That age is not measured in years or centuries, but in intervals so long that each minor impact in interstellar environments gradually accumulates into a layer of trace. No one knows exactly how thick Oumuamua's outer layer is, what molecules it contains, or whether the interior resembles the surface. If humans could bring back a piece of it, examine it under a microscope, separate the outer layer from the inner, and measure each component and structure, the story might be far clearer. The surface could be a shell altered by radiation over long periods, with the interior less touched. Or the entire object might have experienced such a complex history that the outer and inner layers cannot be separated by any simple imagination. But no sample was returned, no spacecraft passed close enough, and its red color could only be read remotely through reflected light, so it must be treated as a clue rather than a final conclusion. Distance makes all information thin, but also gives each clue its own weight. A subtle hue in the data is not like a clear photograph placed before us, but like a faint scent left by someone who has gone far away, not enough to tell their whole story, but enough to know that there is a history behind it. With Oumuamua, the deep red makes the object more than just an open trajectory and a fluctuating brightness. It begins to convey a sense of age, not a precise number to record, but the feeling of a surface that has lived long in space, long enough for its environment to write on it in a script slower than any human story. Within the solar system, such colors often evoke the cold, distant regions where sunlight is far weaker than near Earth. Beyond Neptune's orbit, many icy bodies carry red, reddish-brown, or dark tones, which may result from radiation-altering surface compounds over time. Some comets, when far from the Sun, also have very dark surfaces covered with material processed in the space environment. As they approach the Sun, if the underlying ice warms enough, gas and dust may escape, forming a faint coma or tail. But Oumuamua did not fit that template easily. Its color suggests aging in space, yet as it passed near the Sun, it did not reveal a familiar cometary tail. It is precisely this mismatch that makes it hard to classify. Its trajectory indicates an interstellar origin. Its brightness variation suggests an unusual shape. Its color hints that its surface has undergone long-term effects of the space environment. Yet the absence of a clear dust and gas envelope means it does not resemble a typical comet in a recognizable way. Each characteristic nudges the story in one direction, then the next feature tilts the picture slightly. Oumuamua does not fit neatly into a pre-existing box, and perhaps that is why it forces humans to hold multiple pieces of information together, no single piece amplified into the whole truth, but each piece deepening the object's story. Its reddish color also evokes a question about the journey it has taken. A surface altered over long periods in space may have endured a long time after leaving its original star system, but the color does not reveal when it departed, from where, or under what circumstances. It only indicates that the outer layer is no longer pristine in any simple sense. Perhaps Oumuamua formed in the protoplanetary disk of a young star, where rock, ice, and dust collided to build planets. Perhaps it once belonged to the cold outer reaches of another star system, only to be deflected by a large planet and ejected from its original gravitational family. Perhaps it drifted for eons through interstellar space, long enough for cosmic rays to leave a faint, persistent imprint. Those possibilities fan out like many dim trails in the dark, but none are illuminated all the way back to a starting point. The deep red also reminds us that seeing color does not mean knowing composition. A surface can appear red for many reasons: the types of molecules present, how radiation has altered the material, particle size, surface roughness, or the thermal history the object has experienced. So the red is not a definitive answer, but a clue placed alongside others. It tells us that Oumuamua's surface seems altered, that it seems to have endured harsh conditions, and that its story did not begin in the few weeks of human observation, but perhaps opened long before it entered the sun's light. There is a very gentle encounter in that fact. Before passing through the solar system, Oumuamua existed in regions where our sun was only a distant star, perhaps indistinguishable from countless other points of light scattered across the galaxy. Yet it was precisely sunlight from our sun, a star not its home that allowed humans to see a hint of color on its surface. In a very short segment of its journey, that light touched the interstellar visitor, bounced back to Earth, and became data in a telescope. A star far away from its origin inadvertently helped it be recognized by a small civilization living around that star. If the trajectory is the trace of its journey, the color is like a skin that has carried that journey through time. The path tells us it came from outside. The fluctuating brightness hints that its shape is irregular. The deep red suggests that its surface may have been exposed for long periods to radiation, cold, darkness, and near-empty regions of space. The three clues are not enough to reconstruct the full life of Oumuamua, but they make this visitor less abstract. It is no longer just a symbol or an orbit. It begins to have a path, a form, a color, and a sense of age from a place humans can touch only through light. As soon as the color suggests a surface aged in space, another question quietly arises. If Oumuamua once had ice or volatile material beneath the radiation-altered outer layer, what would happen as it approached the sun? A typical comet often responds clearly. Ice warms, gas escapes, dust is dragged along, and a tail or faint coma may appear around the comet's nucleus. With Oumuamua, astronomers did not observe such familiar behavior. The deep red visitor passed through the sun's light with almost no obvious cometary tail, and it is precisely that absence that leads the story into a stranger layer, where what is unseen can be as significant as what is recorded. A comet is often remembered by humans, not for its tiny core, but for what it reveals when it moves close to the sunday. Far away, a comet may be only a cold, dark body, almost silent against the black background of space. But when its orbit carries it into a warmer region, the ice on or near its surface begins to respond to sunlight. Gas escapes, dust is pulled along with it, a hazy layer spreads around the small nucleus, and then the familiar tail forms under the influence of sunlight and the solar wind. From a quiet object, a comet can become a thin streak of light across the sky, beautiful enough that many cultures once saw it as a special sign in the night. So when a small, cold, dark, deep red object from a distant region passes by the sun, the thought of a comet comes very naturally. In the solar system, comets are often ancient fragments from cold regions, where ice and dust have been preserved over long periods of time. They do not need to be brilliant from the beginning. Many comets only become easy to recognize when the sun awakens the volatile materials inside them. A dark body suddenly seems to breathe. A small nucleus suddenly gains a faint halo. An almost nameless object suddenly leaves behind a long tail, making its path clearer to the eyes of observers. Oumuamua, however, did not fully step into that familiar image. It came close to the sun, passing through a region where an ordinary comet might begin to show clearer activity. But the observations did not reveal an obvious envelope of gas and dust around it. There was no bright tail clear enough to place it immediately into the classic picture of a comet. In the data, it still appeared as a small and rather solitary point of light, without a stretched haze of dust, without a soft glowing trail behind it to say that ice was escaping strongly. This interstellar visitor remained silent in precisely the place where many comets would begin to speak. That silence makes the story harder to classify, but it should not be understood too quickly as a simple conclusion. Not seeing a clear tail does not mean the object must have been completely dry inside, nor does it prove that it had no connection to comets at all. Some comets are only weakly active. Some objects contain very little dust, and in some cases gas may escape without carrying enough solid material with it to create an easily visible coma. A small, faint object moving away as quickly as Oumuamua makes weak signs even harder to catch. The empty space in the images, then, is not a wall closing every possibility. It is more like a blank area that makes people examine the remaining data more carefully. The signs of Oumuamua do not all point neatly in one direction. Its trajectory shows that it came from outside the solar system. Its color suggests a surface aged by the space environment. Its strong brightness variations hint at an irregular shape, perhaps elongated or flattened. Those details make an icy origin not unreasonable, but the tail is absent. It is precisely that mixture that keeps this object from standing still inside a familiar box. It is not simply like a dry, inert asteroid in the easiest sense, yet it also does not behave like an easily recognizable comet. It lies somewhere between those images, where every piece of data is real, but no single piece is enough to tell the entire story by itself. A comet often leaves signs because its ice turns directly into gas when warmed, a process called sublimation. Gas escaping from the surface can carry dust with it, forming a coma around the comet's nucleus. When sunlight and the stream of particles from the sun act on that material, the tail can stretch outward. This image is so familiar that people may easily assume every comet approaching the sun must appear in that way. But nature rarely keeps everything inside neat illustrations. A small object may lack fine dust, may have an outer crust altered by radiation, or may contain volatile materials that do not produce an easily visible glow. Some activity can occur without leaving a clear tail in images. The outer crust of an object that has wandered through space for a long time may become very different from the deeper material inside. Cosmic rays and radiation can make the surface darker, redder, harder, or less reactive when it encounters sunlight for a short period. If ice or volatile materials still exist beneath that crust, they may not escape in the strong, dusty way familiar comets do. They may remain trapped, escape only weakly, or leave the surface in a form that is difficult to observe from far away. In the case of Oumuamua, the short observing window and the faintness of the object made all of these possibilities even harder to separate. There is a very subtle point here. In astronomy, absence is also data. A tail that does not clearly appear is not simply nothing to talk about. It forces people to ask why it did not appear, what the observational limits were at the time, how much dust could have remained hidden, and if gas was escaping, how discreet that gas would have had to be in order not to create an easily visible coma. Questions like these do not make the story drier. They slow it down in the right way, because instead of immediately choosing the loudest explanation, human beings must sit with an absence and see how that absence limits the possible answers. Oumuamua passed through the sun's light with an almost reserved appearance. If it once carried ice within it, that ice did not create a magnificent tail for humans to admire. If anything escaped from its surface, it did not carry enough dust to draw the familiar streak of light. The object was like a visitor breathing very softly, passing through a bright room without making the curtains visibly move. People knew there was a presence, knew it had crossed through, knew it was not entirely like ordinary objects, but they could not point to a tail and say, "Here is the obvious sign of a comet." Because that obvious sign was missing, the other pieces of information began to stand out more strongly. The deep red became the trace of a surface that had endured long-term exposure. The light curve became the sign of an irregular shape. The open orbit became evidence of an interstellar origin, and the absence of a tail became part of the portrait, like a dark region in a painting that can make the bright areas feel deeper. Oumuamua is not made only from what humans saw, but also from what might have appeared and did not. That makes this object different from many familiar comet stories. A brilliant comet can be told through the image of a long tail, through the sense that it wakes up as it comes near the sunday. Oumuamua is told through restraint. It did not flare into a spectacle. It did not open into a large envelope of gas and dust. It did not allow humans to classify it too quickly by sight. It was so quiet that astronomers had to shift their attention from image to motion, from what was not seen in the pictures to what could appear in the measurements. That reserved quality does not make it less fascinating. It makes its mystery finer, harder, and closer to the way real science works. An object without a clear tail would seem as though it should simply follow the path laid out by gravity. If there is no escaping gas, no dust being pushed away, no additional force from the object itself, then its motion should be explained almost entirely by the gravitational pull of the sun and the planets. But Oumuamua did not simply stop there. When its path was measured carefully enough, astronomers noticed a small deviation, a portion of its motion that did not match gravity completely. That deviation was not large, it did not create any dramatic spectacle, but it was enough to bring the question back through another doorway. If there was no tail, could there still have been a form of outgassing too subtle to see? If there was no dusty haze around it, could a transparent gas, or gas with very little dust, still have gently pushed the object as it moved away from the sun? Those questions make Oumuamua stranger in a very quiet way. It did not need a bright tail to change its path slightly. Perhaps only a very small force, acting over the right amount of time, could still leave a mark on the orbit. And if that mark was real, then the missing tail was no longer the ending of the comet story, but a doorway leading to the next question. This interstellar visitor therefore passed through scientific memory with a very distinct presence. It had the color of an aged surface, the changing light of an unusual shape, the trajectory of an object not held by the sun, yet it lacked the tail that many people might expect from an object possibly related to comets. All of this made it feel like a piece of music with several notes left silent, and those silent notes are exactly what make the listener realize the melody is not simple. The question was no longer only why it did not resemble a familiar comet, but whether it was showing a kind of activity more hidden, weaker, or different from what we usually see. By this point, the missing tail had done its work, not closing the explanation, but making the question more precise. Oumuamua did not give humans a streak of light to follow, so humans had to follow its path. And within that path, a very small push began to appear, like an unseen breath on an object that seemed silent. The next part of the story no longer lies in what telescopes saw around it, but in what measurements detected in its motion. A slight deviation beyond gravity, small enough to be easily missed, yet enough to make this interstellar visitor even more unforgettable. An object passing near the sun is never entirely indifferent to its influence. Whether it is a planet, comet, asteroid, or a strange fragment from between the stars, the sun touches its path with gravity. No collision is needed, no dazzling light. Yet the sun's enormous mass pulls on everything around it, curving straight trajectories and nudging distant motions slightly as they pass through its sphere of influence. With Oumuamua, the same effect occurred. It swept through the inner solar system, its path bent by the sun, then continued outward. But when the observations were carefully aligned, that curve did not fully match the familiar rhythm of gravity. The difference is very small, so small that overstating it would rob it of its reality. Oumuamua did not suddenly veer, did not dart in a strange manner, nor did it make anything unusual appear in the sky. It simply left the solar system a little faster than a purely gravitational path would predict. Just a little, yet in astronomy, sometimes a little is enough to open an entire question. For when an object has been measured across multiple positions, when the motion of Earth has been accounted for, when the sun's gravity has been modeled, the remaining discrepancy, however slight, cannot be dismissed. One can imagine a dry leaf drifting on the surface of water. If only the current acts, the leaf follows its flow. But if a very gentle breeze blows across it, the leaf deviates slightly, not enough for a distant observer to notice, but enough for a careful eye to see that the current is not the only force acting. For Oumuamua, the strong current is the sun's gravity. That subtle breeze, if it exists, must be a very weak force generated as the object passed through the light and warmth of our star. For familiar comets, such a force is not unusual. When ice warms, gas can escape from the surface, sometimes carrying dust and forming a faint coma or tail. That escaping gas, though very weak compared with the sun's pull, can gently push the nucleus in the opposite direction. It is like a small breath coming from the object itself, not enough to act like a rocket, but enough to slightly alter its gravity-determined trajectory. For a small object, Even a very gentle breath can leave a trace. But Oumuamua did not provide humans with that simplicity. If it had a clear tail, the story would have been much easier. We would see the dust, see the gas, see the signs of activity, and the small push in its motion would feel more natural. A comet without gassing does not move entirely like an inert rock, and that is nothing unusual. Yet this interstellar visitor revealed almost none of the familiar tail. It passed close to the sun, appearing quiet, faint, and discreet, as if its surface did not wish to offer the spectacle humans were expecting. That contrast deepens the story. In images, it does not resemble a clearly active comet. In its motion, however, a hint suggests an additional force, a small one outside the usual calculations of gravity. Placing these two observations together creates a gap that is hard to ignore. No visible breath, yet the path seems to have been touched by one. No tail, yet the object moves away slightly faster. Oumuamua becomes elusive not because it defies science, but because it does not fully fit the familiar frameworks of science. The question thus becomes more subtle. Could gas be escaping almost without carrying dust? Could a transparent or hard-to-detect substance leave the surface, generating a slight push without forming a visible tail? Could the outer crust, aged by interstellar radiation, allow the underlying material to escape in a way that is extremely discreet as the object nears the sun? Those possibilities do not make Oumuamua mystical. They show that nature can be soft and complex, beyond the neat comet illustrations with a long tail we are used to. A small object is always more sensitive to weak forces. With the same amount of escaping gas, a large body might hardly be affected, while a smaller fragment is pushed more noticeably. Oumuamua did not need a strong outburst, a bright dust tail, or a grand display for telescopes. If material escaped at a very low level over an appropriate period, its motion could still carry that subtle imprint. And because it was discovered late, moving away quickly, fading day by day, these weak signs were even easier to miss in direct observation. This makes the tiny push a very special kind of clue. It does not appear in images, but in the subtle deviation of the path. It does not show up as a streak of light, but in measurements aligned together. It does not reveal where it came from, only that gravity alone did not tell the whole story. There is a very thin portion of motion remaining, like a light drag mark in snow that does not match the steps. One can look at that trace for a long time without knowing precisely what caused it, but one cannot pretend the snow is perfectly flat. Some explanations have been proposed. Some considered the extremely weak pressure from sunlight, though light is not wind in the usual sense. It carries momentum and can push an object. That idea leads to strange images, because for light to have a noticeable effect, the object would typically need very unusual characteristics, such as being extremely thin or lightweight in an unverified way. It is a possibility that has been mentioned, but not a firm conclusion. The less data there is, the more carefully humans must treat enticing explanations, because the most attractive image is not always the one best supported by data. Natural explanations based on outgassing still hold weight, even though they must solve the hardest problem: why no visible dust or tail? Perhaps Oumuamua's activity was weaker than a typical comet's. Perhaps the escaping gas did not carry much dust. Perhaps the outer surface had been altered by space, masking the underlying processes. Later, models even proposed that molecular hydrogen could form and be retained in water-rich ice over long periods of cosmic ray exposure, then escape as the object warms near the sunday. That possibility is appealing because it allows a small push without requiring a clear dusty tail like a usual comet, but it remains a model to be treated with caution, not a closed door to all questions. That subtle push also gives Oumuamua's image a quiet kind of vitality. Not alive as a creature, not purposeful, not sending a message, but alive in the sense that a physical object is still responding to its surrounding environment. It drifted for eons through cold darkness, then entered the light of a star that was not its home. Its surface absorbed heat. Outer layers of material may have expanded, contracted, transformed, or released a very small amount of gas. All of this happened so quietly that telescopes did not see a tail, yet the trajectory preserved a faint trace of that reaction. There is a distinct quality to this type of evidence. It does not overwhelm with imagery, but invites one to lower their voice and examine the small details. An object does not need to shine to be memorable. A path does not need to deviate much to make humans pause. Oumuamua passed by without creating a spectacle, yet in its motion there is a subtle residue, like a door that has just closed while the air in the room still quivers slightly. We do not see the hand that pushed the door. We only know that the door did not close exactly as predicted. Had Oumuamua been discovered earlier, the story of this push might have been clearer. Humans could have tracked it longer while it was closer and brighter, sought weaker gas emissions, better constrained dust levels, measured how the tiny thrust changed with distance from the sun, and checked whether its motion matched any kind of outgassing pattern. But this visitor arrived and departed too quickly. The data we retain is like a short musical excerpt recorded near the end of a song. The final notes are enough to recognize something unusual, but not enough to hear the full melody from the beginning. Thus, the non-gravitational push is not a loud climax, but a narrow doorway in the story. It does not make Oumuamua into something supernatural. It does not allow us to claim that every aspect has been fully explained. It simply forces the preceding clues to be reorganized. The open trajectory, the unusual shape, the deep red color, the absent tail, and now the tiny deviation in motion. Each fragment is subtle, yet when placed together, they reveal an interstellar visitor that is simultaneously real and elusive, grounded in science yet retaining a portion of its own silence. At this point, the question is no longer whether Oumuamua is strange. It already is, in a quiet way that needs no exaggeration. The question becomes, what mechanism could produce such a slight push without leaving the familiar tail? What kind of breath could exist in silence? Could an old, irradiated ice layer retain material inside, then release it when warmed by the sun? It is precisely in that delicate space between what is seen and what is unseen that Oumuamua prepares to lead us toward a far more elegant natural hypothesis than any loud explanation. Perhaps the push comes from a hidden exhalation trapped deep within ice, aged between the stars. Beneath Oumuamua's deep red, almost silent exterior, the answer may lie in something very light. Not a streak of dust stretching across the sky, not a familiar comet tail, not a spectacle easily captured by telescopes. Just hydrogen, a simple, nearly weightless gas that in daily life, humans hardly ever think of as the main character of a cosmic story. Yet in the model proposed to explain Oumuamua's tiny push, it is precisely that faint gas that could have acted as a quiet breath, escaping from within the aged ice as the object passed near the Sunday. To imagine this explanation, we should not picture Oumuamua as a pure chunk of hydrogen drifting through space, because the story is more subtle than that. One possibility is that the object was once a water-rich icy fragment, or at least contained significant water ice in its original structure. During its long journey between the stars, its surface and internal material could have been affected by cosmic rays over vast stretches of time. High-energy particles pass through the ice, interacting with water molecules, altering them, breaking part of the original structure, and producing hydrogen molecules. That hydrogen does not necessarily escape immediately. In the deep cold of interstellar space, it could remain trapped within the ice network, like tiny gas pockets confined in a material that has been dormant for ages. There is something very quiet about that image. An object leaves its home star system, drifting through vast dark regions, with no seasons, no oceans, no atmosphere, only cold, radiation, and time. On the outside, its surface gradually reddens and ages. On the inside, very small changes accumulate over time, producing no light, no sound, no visible spectacle. Cosmic rays are in no rush. Ice does not need to react in a day or a year. The universe has timescales so vast that even very slow processes can matter, provided they are given long enough to unfold. When Oumuamua entered the inner solar system, everything began to change, not through an explosion, but through warmth. The sun did not need to touch the object with fire. Its light only needed to gently heat the surface and near-surface layers as the object passed closer. In an ice mass long processed by cosmic rays, that warming could alter the structure of the ice, like an old material slowly loosening what it had long held tightly. Trapped hydrogen could find a path to escape. There was no need to drag dust along, no need to form a visible coma. Just enough gas escaping in some direction could give the small object a very tiny push. That push is not like the image of an engine. It has no intent, no control, no designed thrust pulses. It is simply the natural reaction of matter encountering new conditions. Old ice that has passed through cold darkness for ages holds hydrogen created by radiation, and when it nears a star, the warmth allows that gas to escape. For a large object, a small outgassing may be almost negligible, but for a small object like Oumuamua, a very gentle escape could be enough to nudge its path slightly away from the purely gravitational orbit. No brilliant tail is needed, no large dust cloud. Just a faint breath can leave a trace in its motion. The appeal of this model lies in how it links two aspects that previously complicated the story. On one hand, Oumuamua experienced a small non-gravitational acceleration, suggesting some form of thrust. On the other hand, it did not show a clear dusty tail like a typical comet. If the escaping gas was primarily molecular hydrogen light and hard to detect and did not carry much dust, the object could be lightly pushed while remaining invisible as a beautiful comet in photographs. This explanation does not require a grand display. It only requires a process subtle enough to match the quiet that Oumuamua left behind. Of course, this remains a model, not a piece of matter we can place on a table for direct examination. No one has retrieved ice from Oumuamua. No one has measured the flow of hydrogen escaping from its surface as it passed near the sundae. What we have are the trajectory, brightness, color, absence of visible dust, and a small deviation in motion. The hydrogen model attempts to weave these pieces into a natural story, a water-rich icy object, processed by cosmic rays in interstellar space, retaining hydrogen inside, and then releasing it when warmed by the sundae. The story is elegant because it does not leave the familiar physics of ice, yet it must be told with the caution of a hypothesis. One can imagine a very old block of ice, not ice from Earth's oceans, but ice that has existed in darkness at extremely low temperatures for extremely long periods. Within it, radiation-induced changes do not appear as large cracks, but as subtle chemical transformations. When the surrounding environment warms, the ice does not simply melt or sublimate as we are used to on Earth. It may rearrange, expand small voids, and release what has been trapped inside. A portion of hydrogen escaping does not necessarily make the object much brighter, but it can carry a small amount of momentum, enough to gently nudge the remaining icy mass along its path away from the sundae. What makes this hypothesis fit with the story of Oumuamua is its subtlety. Many explanations for this object have been drawn toward louder imagery because humans are easily attracted to the most striking phenomena. The hydrogen explanation goes almost in the opposite direction. It suggests that the cause of Oumuamua's slight acceleration need not be some mysterious structure, artificial object, or phenomenon beyond nature, but a small, old, cold, and very ordinary physical process in ice acted on by radiation. The universe does not always require a grand secret to produce something unusual. It only requires very long periods acting on very simple material. In this story, hydrogen is like a memory preserved in ice. Cosmic rays passed through the object when it was still between the stars, leaving unseen alterations. Those changes remain dormant in the cold, not because of intent, but because conditions were not sufficient for them to escape. Then one day, the object passes near a star, not necessarily the one that birthed it, possibly not even the first it ever approached. But the star humans call the Sunday sunlight warms the old ice, and very light molecules begin to leave where they were trapped. A long journey between stars suddenly reveals a small reaction over a few short weeks. If correct, this process explains why Oumuamua could be lightly pushed without leaving a strong cometary signature. Molecular hydrogen is too light and difficult to detect in observations at the time. It does not need to carry much dust to create a thrust. A nearly invisible gas stream could leave the surface, not drawing a clear tail in photographs, yet still quietly alter the trajectory. This makes the absent tail discussed earlier not a complete blank, but a clue that any activity, if present, occurred in a way unlike what we are used to seeing from comets in the solar system. Yet the subtlety of the explanation should not make us forget that it is still under study and debate. All models of Oumuamua must contend with the same challenge. Too little data, too short an observation window, the object already far away, with no chance to return for direct checks. An explanation may be highly reasonable, natural, elegant in connecting the pieces of data, but it does not become absolute truth just because it is compelling. In science, a good hypothesis is not the end of curiosity, but a way to guide curiosity more accurately. The hydrogen model also helps clarify an important point about interstellar objects. They do not need to behave exactly like comets we are familiar with in the solar system. If an icy rock has drifted through interstellar space for a long time, its surface may be deeply altered by radiation. Volatiles near the surface may be lost or hidden. Internal reactions may create components that a younger comet, or one closer to the Sun, would not exhibit in the same way. When such an object passes through our Sun's light, it may act like a comet in one respect, but differ in another. Not because it is mysterious in the sense of being unnatural, but because its history is unlike that of the familiar objects around the Sunday. There is a gentle quality in the way this hypothesis preserves the image of Oumuamua as an old visitor. It does not make the object louder. It makes it older, colder, and more filled with a past. A deep red surface that has passed through time. An unusual body rotating in the dark, a layer of ice that may have been touched by cosmic rays for a very long time, a very faint breath of hydrogen escaping when it met the warmth of the Sunday. All of these details do not create a brilliant spectacle, but they do create a deep image, a wandering fragment of matter carrying within it the history of interstellar space. And then, during one brief segment of its journey, that history acted just strongly enough for humans to measure. When placed beside other explanations, this model also reminds us how science often moves forward in regions where data is limited. Not by leaping toward the strangest possibility, but by asking which natural processes can explain the most with the fewest assumptions. Hydrogen produced inside ice by cosmic rays, then released as the object warms, is one such idea. It does not require Oumuamua to be an object with intention. It does not require unfamiliar technology. It only requires ice, radiation, time, heat, and an object small enough that a faint stream of gas could still leave a mark on its orbit. But the story should not be closed too soon. A beautiful model still needs to be placed under the light of other questions. Can it explain the full strength of the acceleration? Does it fit the size and shape suggested by the light curve? Can it explain why no dust was seen, why no other molecules were detected, and why the surface had the color that was observed? These questions do not weaken the explanation. They keep it in its proper place. A good hypothesis does not fear questions, because questions are what help it become clearer or make room for a better hypothesis in the future. With Oumuamua, there is no path to complete certainty. The object has moved far away. The data cannot be expanded by a return visit. What remains are models placed upon the very small amount of light it left behind. Among them, the image of hydrogen hidden inside old ice has its own quiet beauty, because it makes the tiny push feel natural while still preserving the strangeness of the object. It allows us to imagine an interstellar comet without the familiar tail, an icy rocky body aged by the universe, a nearly invisible breath in place of the bright dust display humans had expected. Perhaps that is what makes this hypothesis fit the nature of Oumuamua itself. Everything about it came to humans incompletely. It did not give us a clear image, only a light curve. It did not give us a home, only an open orbit. It did not give us a comet tail, only a very slight push. And now, a natural explanation also does not arrive as a final voice, but as a quiet possibility. Perhaps inside that aged ice, hydrogen had been preserved over time, and when the visitor came near the sun, a very small amount escaped, enough for its path to carry a faint deviation. A breath like that does not make Oumuamua less mysterious. It only brings the mystery closer to nature, as if behind that tiny push there was not a loud explanation, but the long history of ice, radiation, darkness, and the brief warmth of the Sunday. The object has moved away, so there is no way to return and ask it directly. What remains are a few curves in the data, a few thin signs in the light, and a quiet possibility that beneath that old crust, hydrogen was once held across time and then released just as the visitor passed through our region of light. But the gentler an explanation is, the more carefully it must be held. Oumuamua did not give humans a sample, a close-up image, or a second observing chance to check everything again. It left only enough traces for models to enter, and enough empty space that no model can close the story too early. Perhaps it is there that the beauty of science appears most clearly, not in rushing to say that we understand everything, but in the ability to walk with a natural explanation, listen to it closely, and still leave a small darkness for what remains unknown. Sometimes, a beautiful explanation can feel like a door already open. Everything seems to start fitting together. An ancient object passing through interstellar space, an ice layer shaped by cosmic rays, hydrogen trapped for long periods, and then the gentle warmth of the sun releasing it just enough to produce a tiny push. That story has its own subtle softness, because it requires no noise, no hypothesis too far-fetched, no need to turn Oumuamua into something beyond nature. It only requires ice, radiation, time, and sunlight. Ordinary ingredients, set along a very long journey, can create a phenomenon that makes humans pause. But in science, a gentle explanation does not automatically become the final answer. It may be reasonable, elegant, able to link more pieces of data than other hypotheses, but it must live within the limits of what is observed. For Oumuamua, those limits are clear. The object is far away. No sample exists. No close-up image. No opportunity to point telescopes back at the moment it passed nearest the Sunday. No second chance to observe the same event under better conditions. All humans have is a short segment of data from a visitor leaving the sun's bright region. That is what makes a seemingly simple explanation not simple. If hydrogen escaped from old ice, the amount must be enough to produce the measured acceleration, yet leave no easily visible traces like dust or a comet tail. If the surface was altered by radiation, that layer must match the observed deep red color, while still not completely concealing internal processes. If the object is small and irregularly shaped, the effect of gas escaping on its motion becomes more complicated. An idea may sound light on the surface, but underneath, it carries many questions that must be considered together. One can imagine scientific models like small lamps placed around an object in the dark. Each lamp illuminates a part. One clarifies the orbit, one clarifies the color, one shines on the changing brightness. Another tries to illuminate the tiny non-gravitational push. No lamp is strong enough to illuminate all of Oumuamua. When many are placed together, its shape becomes clearer, yet some shadows remain. A good model is not a lamp turning night into day. It is a lamp that makes the darkness a little less ambiguous. That is why scientists must maintain the distinction between what is measured and what is being interpreted. Open orbit is data, varying brightness is data, red color is data. The absence of a clear tail is also data in its own right. Small non-gravitational acceleration is a result derived from measurements of motion. The story of hydrogen and old ice is a way of arranging these pieces of data into a natural mechanism that can be understood. It is notable because it connects many separate pieces, yet the gap between data and mechanism is where science must proceed slowly. Part of the difficulty lies in the nature of Oumuamua itself. The object is too small and too distant for telescopes to resolve its surface. Weak brightness limits each measurement. Short observation time makes it difficult to separate different possibilities. If it rotates in a complex way, the illuminated area and direction of gas release can change over time. If its shape is elongated or flat, the way even a small force acts on its motion is no longer simple as with a near-spherical body. Those details may seem small, but with scarce data, each minor detail can tip a model in a different direction. In a normal story, humans often prefer neat solutions. A slightly accelerating object might be escaping gas. No visible tail. Maybe the gas is transparent or carries little dust. Red surface. Maybe it has been altered by radiation. Each statement sounds reasonable, and together, they create a smooth narrative. But science does not only ask whether an explanation sounds plausible. It asks whether it holds up against numbers, fits observational limits, explains what has been seen without creating too many unknowns. A good explanation must not only be beautiful in imagination, it must withstand the cold rigor of data. This does not make the story less beautiful. On the contrary, it deepens the beauty. There is a precious calm in not rushing. Oumuamua passed too quickly, but human thinking need not hurry. The less the object leaves behind, the more carefully we must treat what remains. A light curve should not be forced into a shape more definite than it allows. A red color should not be turned into a known chemical component. A tiny push should not be inflated into an extraordinary story. Yet, neither should it be rendered meaningless. Each piece must retain its proper weight. A good natural explanation is like a delicate bridge spanning a region of sparse data. It allows one to go from what is measured to what might have happened. But the bridge is not solid ground. Those crossing it must know there is still empty space below. The old ice hydrogen model can be such a bridge. It carries us from slight acceleration to a subtle outgassing mechanism, from aged color to a history of cosmic radiation, from absent tail to the possibility of a faint gas release without dust. That bridge is beautiful because it does not exaggerate, but it must still be seen as a bridge, not as the far bank already reached. It must also be remembered that Oumuamua did not come to humans in a prepared laboratory. It did not lie still for us to test each hypothesis, change each condition, and remeasure every reaction. It is a fleeting astronomical event. Nature had conducted its experiment long before we knew it existed, leaving only the results in a few images, a few measurements, and a very short interval on the sky. We cannot choose sample size, cannot choose viewing angle, cannot ask the object to rotate slower, shine brighter, or linger longer. Therefore, every model of Oumuamua must carry a measure of humility from the outset. This humility is not weakness. It is a form of scientific strength. A sensational story may crave strong, quick, decisive statements, but the universe does not need to indulge that desire. Some things can only be expressed in terms of confidence, capability, models, and limits. Words like might, suggests, consistent with, uncertain sound softer than bold declarations, yet they keep the story from straying from reality. With Oumuamua, those soft words do not diminish its allure. They make the object feel real. Once that is accepted, the story of Oumuamua is no longer a race to affix a final label. It becomes a lesson in how humans read rare events, A first confirmed interstellar visitor does not necessarily provide enough data to fully understand. Perhaps the next object will be clearer. Perhaps a future sky survey will detect another visitor earlier, while it is still approaching the sun, allowing longer observation. Perhaps then today's models will be tested better by a new case. Oumuamua has passed, but it may have helped prepare us for future encounters. In the darkness between the stars, countless small objects are probably drifting along unnoticed journeys. Some may be dry rock, some may be ancient ice, some may carry radiation-altered reddish surfaces. Some may occasionally pass near a star and release a little gas in silence. Oumuamua is but a tiny sample of a population humans are only beginning to touch. With only a first example, understanding it is difficult because we have few objects to compare. A single strange leaf falls in the yard, hinting at a whole forest, but one leaf cannot describe the forest fully. Perhaps the takeaway is that a simple explanation can still contain many layers. Hydrogen release from old ice sounds gentle, almost peaceful, yet to hold that image, it must pass through orbit, temperature, radiation, ice structure, object size, shape, spin rate, and observation limits. Each layer added does not diminish the beauty. It only shows that the beauty lies not in ease, but in how many natural factors can come together at the right moment to create a tiny sign along the path of a strange object. In that slowness, Oumuamua becomes a story not just about an object, but about how science stands before the insufficiently known. It does not deny the mystery, it does not worship it. It approaches, measures what can be measured, constructs models just enough, and leaves the unknown intact without turning it into legend. A solution like hydrogen in old ice can take us far, but even then it leaves a thin mist ahead. That mist is not meant to unsettle the listener. It only reminds us that the universe is larger than any first answer. And in the place where that mist still covers the story, another type of curiosity begins to emerge. Not the curiosity to find the most attention-grabbing answer, but the curiosity about how humans should approach an object whose data is sufficient to be intriguing, yet insufficient to close the story. Some hypotheses must be kept in discussion. Some must be set down gently because they demand too many unseen conditions. And some hypotheses, even famous among the public, must be examined by the same slow measure, the measure of evidence, of caution, and of the distance between imagination and what the sky has truly left behind. As Oumuamua departed from the solar system, it carried with it more than just its fading light. It left behind something that spread faster than any measurement: human imagination. Within observatories, data continued to be checked by small numbers, by errors, by light curves, by orbits, and by natural models. But outside astronomers' offices, the story began to follow a different rhythm. An object from between the stars, with a possibly strange shape, no obvious cometary tail, and departing slightly faster than predicted by gravity alone. This alone was enough to stir humanity's most sensitive question. What if it isn't just rock or ice? That question does not arise from naivety. It arises because the sky always holds space for possibilities beyond everyday life. Long before exoplanets were known, humans wondered if those distant stars were merely distant points of light, or if they too hosted their own worlds. Before telescopes were precise enough to see evidence, imagination led the way not as an adversary to science, but as a small lamp daring humans to ask. Without imagination, many searches would never have begun. Yet imagination has a dangerous habit. It tends to run ahead of the data, especially when the data leave large gaps. Oumuamua created exactly this kind of gap. It arrived and left too quickly. It offered no close-up images. It provided no clear tail to neatly classify it among comets. It gave no definite shape, only a fluctuating light curve suggesting an unusual body. It left no simple answer for the tiny non-gravitational push, only models under review. Those gaps are like dark areas between strokes in a drawing, and the human mind is quick to fill them with a larger image, a piece of technology, a solar sail, an artificial object drifting through interstellar space. Such ideas were suggested because they touched multiple strange points at once. If an object were extremely thin or light, sunlight could push it in a noticeable way, like a very light wind moving a large sail across water. Without a clear cometary tail, it is natural to wonder whether the small push truly came from outgassing. If its shape is unusual, imagination gains even more room to stand. From there, the image of a solar sail drifting between the stars became famous, not because it had been proven, but because it linked the unknown into a compelling narrative. But evocative ideas are not evidence. A hypothesis can be beautiful, bold, even worthy of consideration, but it must still pass through the same narrow gate as any other hypothesis: what the sky actually leaves behind. For Oumuamua, no artificial signal was recorded, no message, no controlled light, no motion alteration indicating clear intent, no close-up images to reveal a constructed structure, no material samples. All that exists is a faint object, an orbit, a color, a light curve, an absent tail, and a small acceleration. Those data allow questions, but are insufficient to turn an artificial explanation into a conclusion. The distance between not yet fully understood and, therefore it must be technology, is vast. In the history of science, that gap has appeared many times. Signals once received steadily led some to briefly imagine artificial origins, only later understood as rapidly spinning neutron stars. Explosions in distant space appeared mysterious until gradually placed within the context of dying stars, black holes, neutron stars, and extreme physics. The universe has shown repeatedly that it can be strange, yet still natural. The unexplained does not automatically invite the most sensational hypothesis. Even so, there is no need to dismiss questions about extraterrestrial intelligence. That question is too large to be treated lightly. The galaxy has hundreds of billions of stars, many with planets, and the elements for life are not exclusive to Earth. Humanity's desire to know whether it is alone is a profound intersection of science, philosophy, and emotion. Only because that question is so vast, it deserves protection from premature answers. If every unusual object were immediately attributed to aliens before natural explanations were sufficiently considered, the weight of the big question would be lost. A fairer narrative lets the artificial hypothesis appear, but does not allow it to dominate the sky. It can stand alongside models of ice, hydrogen, radiation, shape, light pressure, and outgassing, each subjected to the same scrutiny. The more extraordinary an idea, the greater the burden of evidence. If Oumuamua were a solar sail or an artificial structure, the object would need extremely specific traits: thin or light enough to be pushed by sunlight, durable enough to survive interstellar travel, consistent with observed color and reflective pattern, and leaving no other detectable signs. Those requirements cannot be fulfilled by the mere impression that the story sounds compelling. Meanwhile, natural explanations, though not perfect, start from the universe's known ingredients. Ice exists, rock exists, cosmic radiation exists, small irregular objects exist, outgassing from comets exists, very slight pressure from light exists. The task is to arrange these elements in the way that best fits Oumuamua's sparse traces. A model like hydrogen trapped in old ice does not require invoking an unproven civilization. It still carries its own questions, but it follows the familiar path of physics: small processes, accumulating over long periods, producing just enough effect under special circumstances. The fascination of Oumuamua lies not in its potential as proof of a distant civilization. It is compelling even as a natural object, a piece of matter leaving its star system, drifting through the dark between stars for a long time, passing by the sun, and leaving a trail of clues that are hard to piece together. This alone is profound. Nature is not impoverished by the absence of design. On the contrary, a completely natural object that still prompts deep reflection shows how vast the universe is and how ordinary processes, given enough time, can appear extraordinary. Perhaps what made the alien hypothesis popular was not just the data, but the awakening it triggered in humans. An object from between the stars passing near us, and for a brief moment, the distance between earthly life and the rest of the galaxy seems thin. Minds wonder if there is anyone at the far end of the darkness. Not everyone asks this in scientific terms, but the feeling is profoundly human. If something can come from another star system, the sky ceases to be a distant backdrop. It becomes a space with paths, exchanges, potential encounters, even if that encounter is only a lifeless icy rock passing by. Maintaining that feeling without losing accuracy is the hardest part. Denying imagination entirely makes the story cold. Letting imagination run too far detaches it from the data. Oumuamua requires a middle rhythm. One can acknowledge that artificial possibilities were proposed and intrigued the public, while also stating clearly that current data are insufficient to view it as proof of extraterrestrial technology. These 2 points are not contradictory. An idea can be worth mentioning without being central to the explanation. Seen this way, the extraterrestrial hypothesis resembles a slightly open door at the end of a corridor, not a fully explored room. One can see a faint light inside. Be curious. Be reminded that the universe holds countless unknown possibilities. But one should not step through that door and claim to have seen the entire house. Oumuamua does not grant that authority. It presents a strange object and leaves before humans can ask too many questions. When the loud stories settle, the remainder of Oumuamua is still substantial. No artificial signal is required for it to be the first confirmed interstellar object to pass through the solar system. No alien civilization is needed for it to demonstrate that the region around the sun is not closed and that fragments from other star systems can visit. No need to make it a spacecraft. It still compels humans to think about wandering objects between stars, how planetary systems eject material, and rare encounters that could be missed without patient observation of the sky. A natural mystery kept at its proper scale can sometimes endure longer than an oversized explanation. It does not flare and fade with excitement. It remains slowly, like a small stone in the palm, revealing more veins the longer one looks. Oumuamua is the same. If we forced it to be a message from someone, we might overlook the message nature had placed in it. That the galaxy does not stand still in isolated islands, that matter can leave one star system and drift into another, and that a faint point in the data can expand our model of the universe. Thus, the story of the extraterrestrial hypothesis should be told in a quieter voice than sensational headlines, not to make it less compelling, but to place it at the right distance. At that distance, imagination still has room to breathe, but it does not obscure the data. Caution remains firm, without stifling the sense of wonder. Oumuamua need not carry intent to be a messenger. It communicates through its existence, its trajectory, and by reminding humans that fragments from faraway places can cross the light of our star. If one day humanity truly finds evidence of extraterrestrial intelligence, that evidence will need to be far clearer, an unmistakable signal, a structure that cannot be explained naturally, a data sample strong enough to surpass all simpler explanations. When that day comes, it will be among the greatest moments in human understanding. But Oumuamua does not need to shoulder that moment. It has its own role, opening the first door to interstellar objects, reminding us that the sky contains more than solar system members, and teaching us how to live with a question without immediately needing an answer. By returning the artificial hypothesis to its proper place, the story becomes calmer. There is no need to argue between certainly natural and certainly technology. There is only a passing visitor, some reliable traces, a few natural models being tested, and a small space for further possibilities not yet demonstrated. That calm suits Oumuamua itself. It did not arrive with noise. It did not depart with a greeting. It left no proclamation. It merely gave humanity a chance to practice the hardest thing when looking at the universe: curiosity without haste, imagination without leaving the evidence behind, and the acceptance that some questions are more beautiful unanswered. Oumuamua has long since moved away, but in human data, it still leaves a few traces clear enough for the story not to dissolve into darkness. No close-up image was returned by a spacecraft. No sample rests inside a laboratory. There was no second chance to observe it when it passed closest to the Sunday. That visitor arrived late in our field of view, then quickly faded as it left the solar system. But even though the encounter was brief, it left behind a very real set of signs: its trajectory, its brightness, its color, the absence of a familiar tail, and a small deviation in its motion. First is the trajectory. This is the clearest trace, and the reason Oumuamua became different from the very beginning. It did not orbit the sun like a planet. It did not return periodically like many comets. It was not following a long orbit that was still held by the gravity of our star. It entered the inner solar system, had its direction bent by the sun, and then continued leaving the system. That path was like an open stroke drawn through space, a point of entry, a brief passage through the light, but no loop back. Because of that trajectory, astronomers realized this was not a familiar object that had long lived within the sun's family. Even so, the trajectory does not tell its entire past. It shows that Oumuamua came from beyond the solar system in terms of its motion, but it does not lead straight back to a specific parent star. In the Milky Way, everything is moving. Stars drift along their own orbits around the galactic center. The sun is moving as well. A small object like Oumuamua may have wandered through space for a very long time, and even a tiny uncertainty in its speed or direction can make its origin blur across millions of years. So the certainty lies in the encounter itself, while its original home remains beyond our reach. Its light left another sign, weaker, but very important. As Oumuamua rotated in space, its brightness changed strongly. At times it reflected more sunlight, at other times less, as though each rotation turned a different side of the object toward the telescope. From that rhythm of brightening and dimming, astronomers inferred that it may not be round, not even, and perhaps had an elongated, flattened, or distorted shape. But this inference is not an image. No one saw its true outline. Illustrations of a long, dark object or a thin, flat one are only human attempts to place an image over the data. The data itself only says that its brightness varied more than a near-spherical body would usually produce. Oumuamua's color also does not stand alone. It appears reddish, subdued, and dark, like many surfaces that have been altered for a long time by the space environment. An object drifting between stars can have its outer layer changed by cosmic rays and ultraviolet radiation over time. Compounds on its surface may become darker, redder, and carry the aged look of matter exposed to cold darkness. But that red color is not a complete chemical analysis. It does not say exactly what lies inside the object, does not reveal the ratio of rock to ice, and does not point to one single history. It only adds another layer. The surface of this visitor does not seem new, clean, or bright, but touched by space long enough to carry an older shade. Then there is the tail that did not clearly appear. If Oumuamua had behaved like a familiar comet as it passed near the sun, one might have expected gas and dust to escape, forming a faint coma or tail. But observations did not show that sign in an easily recognizable way. The object passed close to the sun, while still appearing almost solitary in images. This once made it seem more like an asteroid than a comet, at least in the first impression. But the absence of a tail does not automatically mean that nothing escaped from it. A very small amount of gas, with little dust or difficult to observe, could still exist without leaving a familiar streak of light across the sky. Its motion is what makes the story difficult to close. When its path was measured more carefully, Oumuamua did not move exactly like an object affected only by gravity. It showed a very small acceleration beyond the pull of the sun and planets. Not a major turn, not a motion with intention, but a thin deviation in its orbit. With comets, this can often come from gas escaping the surface and creating a gentle push. But with Oumuamua, the tail did not clearly appear, so the explanation must be more subtle. If gas was escaping, it had to be doing so with little dust, more weakly, or in a way harder to see than in ordinary comets. From those signs, the model of hydrogen in old ice becomes noteworthy. In this picture, Oumuamua may have contained water-rich ice that was affected by cosmic rays during its long journey between stars. Those effects could have produced molecular hydrogen trapped within the ice structure. When the object passed near the sun, warmth changed the ice and released hydrogen, creating a small push without necessarily carrying dust along to form an easily visible tail. This is a natural explanation, quiet and much more economical than louder hypotheses, but it still does not become absolute certainty. No one directly measured that flow of hydrogen. No one has a sample of Oumuamua's ice to test. So the portrait of Oumuamua does not appear as one continuous outline, but as several layers of measurement placed beside one another. Its orbit shows that it is an interstellar visitor. Its brightness suggests an unusual shape. Its color hints at a surface aged by space. The lack of a clear tail makes the ordinary comet model more difficult. The slight acceleration forces people to consider some additional force. These pieces do not contradict one another, but they also do not combine into a simple answer. They create a real object, with real data, yet with many gaps still lying between the data points. Those gaps are exactly why Oumuamua should not be told as a completely empty mystery, nor as a problem already solved. Some things are certain enough to keep. Some things should only be spoken of as possibilities. Some things still cannot be known from the current data. The object has moved far away, so humans cannot return to the best moment for observation. Every model now has to work with the small amount of light it left behind, and with the limits of an encounter that happened almost later than we would have wished. In the middle of this journey, Oumuamua feels more like a first case than a final answer. Before it, scientists already had reasons to believe that interstellar objects could pass through the solar system. After it, that was no longer only a prediction. A real object had been discovered, measured, named, and followed until it became too faint to continue. But the first example is rarely the perfect example. It arrived unexpectedly, was recognized after it had already left the most favorable position, and left less data than humans wanted. In return, it made one thing clear: the next encounters need better preparation. If another interstellar visitor is discovered earlier, the story could be very different. Telescopes could follow it longer. Weak gas signals could be searched for more carefully. Its color and brightness could be measured across more stages. Perhaps one day, humans may even prepare space missions fast enough to chase an object from another star system. Oumuamua did not give us that chance, but it showed why such a chance would be worth pursuing. It revealed a gap in human observational ability, while also opening a new target for the astronomy of the future. That object, then, was not only a strange dot in the data from 2017. It was a real reminder that the solar system is not completely separate from the rest of the galaxy. Young planetary systems can eject fragments of rock and ice. Those fragments can drift between the stars for long periods of time. Most are probably too small, too dark, or pass too far away for humans to notice. But sometimes, one of them passes close enough, bright enough, and at the right moment, while an observing system happens to be looking in that direction. When that happens, an anonymous object from very far away can become data, and then become a question. Looking back at what remains, Oumuamua does not need to be made larger through exaggeration. It is already special enough in its smallness and elusiveness. It showed a real interstellar trajectory. It showed that an object too distant to be imaged clearly could still reveal hints of its shape through brightness. It showed that color can carry traces of time in space. It showed that absence, too, can be data. It showed that a very small push can force natural models to become more subtle. And more importantly, it showed that humans are only beginning to learn how to read visitors from between the stars. When all the signs are placed beside one another again, the story becomes clearer in a humble way. Oumuamua did not give us a complete portrait, but it did not leave empty-handed either. It left enough to show that the encounter was real, enough to reveal that the object did not belong to the familiar paths around the sun, enough to raise questions about its composition, shape, and history, but not enough to close the mystery completely. From that position, the journey can expand beyond a single object, toward the larger question of fragments of matter thrown from their homes and left to wander silently through the galaxy. The traces left by Oumuamua lead to a very practical question. If it does not belong to the solar system, how did such an object leave its birthplace? It could not simply appear in interstellar space, as if it had no past. Before becoming the visitor passing through the sun's light, it must have once been part of some environment, around a young star, in a cold region filled with rock and ice, or within a planetary system mature enough that small objects could be pulled, pushed, collided, and have their paths altered. Oumuamua does not tell us which stellar system that was, but its trajectory forces the story back toward the possible origins of wandering interstellar fragments. A young planetary system is not stable from the start. Around a newly formed star, there is usually a disk of material gas, dust, ice, and small particles rotating in a wide region. Within this disk, particles collide, stick together, grow into pebbles, rocks, and then larger objects. Some continue to accumulate matter to become planets. Others remain as debris, small fragments that are not large enough, not in the right location, or are nudged by larger objects. Looking at a mature planetary system, we often see the planets as the main members, but behind them lies a long history of fragments that never became full worlds. Within that history, the gravity of large planets can play a strong role. A giant planet does not just orbit its star, it can alter the paths of small objects passing nearby. If a rock or ice fragment comes too close, the planet's gravity can pull it onto a new orbit, fling it inward, push it outward, or in some cases give it enough velocity to escape its original system. No explosion is needed, no spectacular event, just a close gravitational encounter. After such an encounter, a fragment that once belonged to a star system can begin a journey with no path back. This is how interstellar objects become tangible. They do not require a mysterious origin. They can be byproducts of the formation and rearrangement of planetary systems. When giant planets clear their orbital zones, when small fragments collide and scatter, when a young star system gradually stabilizes, much material can be lost from the system. These fragments do not disappear. They simply leave the star that once held them and enter the wider interstellar space. There, they become cold, dark, hard to detect objects moving through the galaxy, no longer belonging to any one Sunday. Our own solar system demonstrates how strong the gravity of large planets can be. Jupiter can alter the orbits of comets and asteroids. Neptune can affect distant objects. Over very long timescales, the giant planets may have stirred, moved, or ejected many fragments from their original positions. This does not mean every detail is simple, but it shows that a planetary system losing material is not unusual. If other star systems go through similar, chaotic stages, the galaxy may contain countless fragments of rock and ice expelled from their home systems. Oumuamua could be one such fragment, but caution is needed. We do not know which star system it came from. We do not know whether it was ejected by a giant planet, a collision, or another process in the original system. We do not know how long it wandered before passing the Sunday. What can be said safely is that natural mechanisms for producing an interstellar object like Oumuamua are entirely plausible. A fragment of rock and ice could form in a planetary system, be ejected, and drift through space for a very long time before incidentally passing near another star. For most of that journey, such an object is nearly invisible. It does not shine on its own. It only reflects light when a star is close enough. Between stars, light is too sparse, and distances too vast for small fragments to be detectable. Even when passing near a star, if the distance is still large or the fragment is too small, telescopes may not notice. Oumuamua was seen only because it passed close enough, was bright enough, and at a moment when humans had survey systems capable of recording a faint moving point of light. This gives the 2017 discovery broader significance. Oumuamua was not just a single odd object. It was evidence that at least one fragment from outside the solar system had passed through our observational window and was recognized. One object alone cannot tell us what interstellar objects generally look like, what their compositions are, or how comet-like they behave. But a single object is enough to open a new field of observation. Before it, interstellar objects were predicted. After it, that prediction had a real example. Looking more closely, Oumuamua also invites us to rethink the concept of home in the universe. A fragment could form near a star, remain in orbit for a time, then be ejected from the system. From that moment, it no longer experiences days or years in the old sense. It no longer follows seasons around its original star. It simply moves through the wider environment of the galaxy. Its surface may be altered by cosmic radiation. If it contains ice, the outer layer may age, harden, or change composition. What was once a small part of a planetary system gradually becomes an interstellar object, carrying traces of both its origin and its journey away. This is why Oumuamua can seem both comet-like and unlike any familiar comet. A comet in the solar system has its own history around the sunday. An interstellar object may have experienced different environments, timescales, and surface conditions before approaching our star. If the outer layer has been altered by radiation for a long time, it may respond weakly or subtly when warmed by the sunday. If the object is small and oddly shaped, even a small amount of gas can slightly alter its motion. These factors do not prove exactly how Oumuamua was created, but they help its observed features cohere. A star system does not need to send material outward with any intent. There is no set path from one system to another. There is only gravity, collisions, motion, and time. A small object ejected outward is not aiming for the solar system. It simply continues along a new orbit, moving with the galaxy. If, after a very long time, it happens to pass near another star, that is the result of natural motion, not an appointment. Oumuamua passed through our region in just such a way, without stopping, leaving little behind, but enough to demonstrate that interstellar flybys can happen. This perspective brings the discussion back to the main point. Oumuamua makes us ask not just whether it is rock or ice, long or elongated, comet-like or not. It makes us ask how many such fragments the galaxy contains. If planetary systems routinely eject large amounts of leftover material during formation, interstellar space may not be completely empty. It remains very sparse, very dark, very difficult to observe, but may contain countless small fragments traveling long distances. Most will never be named by humans. A few, if they pass close enough and are detected at the right moment, may become data like Oumuamua. This also reminds us that our solar system is not an absolutely closed system. It exists within the galaxy, amid larger flows of motion, where material can leave one star system and drift into the vicinity of another. Somewhere out there, fragments that once belonged to the solar system may also be wandering among the stars. If a distant civilization ever observed one of them, it too would be an interstellar visitor from their perspective. This way of thinking requires no exaggeration. It simply places Oumuamua in its natural context, a small part of the very slow, very random exchange of material between star systems in the galaxy. Therefore, this chapter should not stray too far from Oumuamua itself. It is not a separate lesson on planet formation. It only needs to show a plausible path by which a fragment could move from its parent star system into interstellar space. A disk of material around a young star produces countless small fragments. Large planets and collisions alter their orbits. Some are ejected from the system. Those fragments drift for very long periods, altered by space along the way, and sometimes pass near another star. Among them, one fragment passed through the sun's light and was named Oumuamua. From a single instance, humans cannot know the entire population of interstellar objects. Oumuamua may be unusually extreme, or it may be fairly typical compared with as yet undiscovered objects. It may be drier, redder, longer, weaker in activity, or simply the first example that does not fully represent the population. To understand more, we need more examples. Future visitors will show whether Oumuamua is rare or just the first face of a much larger stream of objects. Placed within that broader picture, Oumuamua still retains its central role. It is not diluted into a general lesson about planetary systems. Instead, it becomes a gateway to a larger question. Where can material ejected from its home star go after leaving? That question takes us into interstellar space, often imagined as an almost empty void. But if objects like Oumuamua can exist, then that void is not completely empty. It may be very sparse, very dark, nearly silent, yet still contain material in motion, dust, gas, cosmic rays, and small unnamed visitors. If Oumuamua was ejected from a star system, the longest stretch of its story did not occur while passing through the solar system. The longest stretch was the time before that, drifting between stars in regions so dark and sparse that they defy everyday experience. From Earth, we often look at the night sky and see stars as isolated points of light. Between those points is darkness, and it is easy to assume that this darkness is nearly empty. But interstellar space is not a perfect void. It contains far less matter than any environment familiar to humans, yet still holds gas, dust, radiation, magnetic fields, cosmic rays, and likely countless small fragments moving unseen. An object like Oumuamua, once leaving its original star system, does not enter a perfectly clean room. It enters the interstellar medium, where material density is extremely low but not zero. There are sparse hydrogen atoms, helium, dust grains, far smaller than sand, molecules in denser clumps, and high-energy particles from distant cosmic events continuously passing through. Compared to Earth's air, the environment is astonishingly empty. Yet for an object drifting for millions of years or longer, even these rare interactions have time to accumulate. This is what makes Oumuamua's journey more than just a body moving through nothingness. If its surface appears reddened, if the outer layer seems aged by time and radiation, then the interstellar environment itself is part of the story. Cosmic rays can penetrate material, altering molecules on or near the surface. Ultraviolet light from distant stars, though much weaker than sunlight at close range, may contribute to slow changes. Tiny dust grains, colliding over long timescales, can also affect the surface. None of these processes produces a dramatic spectacle, yet all can leave subtle traces over cosmic time. The interstellar environment also helps explain why an object traveling from one star system to the vicinity of another may differ from the comets we know. A solar system comet may have existed for eons in distant regions, yet remains within the narrative of the Sunday. An interstellar object may have departed its star, drifted through vast cold darkness, endured cosmic radiation over a different time span, and only incidentally passed near the sun for a very short interval. Its outer layer may have changed enough that its reaction to solar warmth no longer matches what we expect from a typical comet. Interstellar space is vast, but it is not still in the sense of being motionless. Stars themselves orbit the center of the Milky Way. Large clouds of gas may drift, collapse, and form new stars. Interstellar dust and gas are pushed, compressed, ionized, heated, or cooled by various energy sources. Supernovae, stellar winds, star-forming regions, and the galactic magnetic field all contribute to structure in this medium, though that structure is far too diffuse and vast for the human eye to perceive. In a photograph of the sky, the darkness between stars may seem like empty space. In reality, it is a physical environment, extremely thin, yet far from meaningless. For a small object ejected from its parent star system, that environment does not provide a clear, signposted path. It does not guide the object anywhere. Oumuamua may have traveled through space by inertia and gravity, influenced very subtly by distant stars, by the general motion of the galaxy, and by occasional passages through regions containing some material. For most of its journey, it likely remained too far from any star to be visible. It was merely a dark, cold body moving through a space far larger than any map familiar to humans. This is why detecting an object like Oumuamua is so difficult. We only see it when it enters the sun's light and reflects enough photons back to Earth. Before that, for the majority of its interstellar journey, it was nearly invisible to us. Had it passed at a greater distance, or been slightly smaller, or at a time when sky surveys were less sensitive, it might never have been recorded. This makes the question of the number of interstellar objects all the more compelling. If only one was detected in a brief window, how many others have passed by unnoticed? The answer cannot yet be known with certainty. A first detection is not enough to measure an entire population. Yet the appearance of Oumuamua shows that such objects exist, and after it, humans have even more reason to believe that interstellar space can contain many fragments of rock and ice ejected from planetary systems. Most are too faint to observe directly. They do not appear in telescopes like stars. They only have a chance to be detected when passing near a bright source, near active survey systems, and moving in an unusual enough trajectory to be recognized among countless other points of light. This makes the interstellar environment a real part of the story, not just a backdrop. If small objects can drift there for long periods, that environment will influence them. A chunk of ice may lose volatile materials from its outer layer or retain others within a modified structure. Its surface may darken and redden. An outer shell may differ from the interior. When that object approaches a new star, its reaction may differ from that of a younger or fresher object, not previously processed by interstellar space. For Oumuamua, this helps contextualize previous clues. Its reddish color, lack of a visible tail, and small non-gravitational acceleration could all relate to a long history before entering the sun's vicinity. Interstellar space is not like a dense ocean where a small object would quickly erode. It is too sparse for that. A fragment can drift for very long periods while maintaining most of its size, especially if it avoids passing through denser regions or colliding with large bodies. But sparse does not mean ineffectual. Over long times, radiation can accomplish what large collisions do not. It does not shatter the object suddenly, but gradually alters the surface. This aligns with how Oumuamua appeared in the data, not as a rapidly disintegrating body, but as a small fragment slowly weathered by space. Thinking of the interstellar environment this way, Oumuamua becomes less like an object isolated from everything. It is the result of multiple stages: formation somewhere, ejection from its original star system, drifting through interstellar space, exposure to radiation and time, and finally passing near the solar system closely enough to be detected. Each stage leaves its own signature, but none is directly observed. There is no footage of its ejection, no device following it between stars, no surface sample to measure cosmic exposure. Everything must be inferred from the few traces left when it passed near us. This does not distance the story from Oumuamua. On the contrary, it grounds the evidence in the environment where it may have been created. Observing it for only a few weeks near the sun, one might forget that most of its history lies elsewhere. Its color is not just the observed hue at that moment. It may reflect a long journey. The absence of a tail is not only a feature of its perihelion passage, it may relate to a surface altered long before. The slight acceleration is not just an anomaly in its orbit. It may be the final response of a material structure shaped by the interstellar medium long beforehand. On a larger scale, interstellar space is where objects like Oumuamua can become natural samples of distant planetary systems. They are not sent for study, yet if they pass close enough, they can carry traces of their birthplace and journey after ejection. A chunk of ice expelled from a cold region around another star could preserve compositions unlike solar system objects. A rock from an inner region of another system might bear a collision history of its own. A surface reddened by interstellar exposure may tell of long durations away from starlight. Oumuamua does not yet provide enough information to read all of this, but it shows that such ideas are within reach of observation. In the future, new sky surveys may discover more interstellar objects, and with more examples, the story of the medium between stars will become clearer. If one object has a clear cometary tail, another is dry and red like Oumuamua, and yet another has entirely different composition, humans will begin to perceive the diversity of fragments ejected from star systems. Then, Oumuamua will no longer carry the full weight of the question alone. It will be the first case in a growing list, a starting point for studying the silent drift of objects across the galaxy. Until more data are available, the most practical approach is to treat the interstellar environment as an essential part of the picture. Space between stars is extremely empty compared to any environment on Earth, but not absolutely void. It contains enough matter to form gas clouds, enough dust to obscure light in denser regions, enough radiation to alter the surfaces of small objects, and possibly enough wandering rock and ice fragments that occasionally one passes through another star system. Oumuamua is a reminder that the darkness between stars is not just distance. It is also an environment through which matter travels, ages, changes, and occasionally leaves a fleeting trace in our data. From here, the story can gain another layer while keeping Oumuamua at the center. If interstellar space is not completely empty, then detecting the first confirmed interstellar object changes how humans view the sky. We may once have thought star systems were isolated, each retaining its matter in its own orbit. But a visitor like Oumuamua shows that movement between systems does occur, rare though it may be in our view. It does not make the galaxy crowded like a city street, but it makes the darkness between stars feel less empty in human understanding. Before 2017, interstellar objects existed in astronomers' calculations as a very plausible possibility. If planetary systems could form from dust, rock, ice, and gas, and if massive planets could stir up the smaller bodies around them, then some fragments would be ejected and drift through the galaxy. Yet a prediction is different from a detection. Oumuamua shortened that distance. It turned the idea of an object from outside the solar system into a measurable point of light, with a calculable trajectory, changing brightness, a color signature, and a name. From that moment, sky surveys gained a new capability. Most of the small points moving across the star field remained familiar: asteroids, comets, fragments from the solar system. But among those ordinary points, sometimes a different object could appear. It might first look like a faint, unremarkable dot in initial images, yet its motion would tell a different story. If the trajectory is open, if the speed is too high, if the sun bends the path without capturing it, the object could be a visitor from interstellar space. The practical lesson from Oumuamua is that observation time is precious. It was recognized after it had passed perihelion, when the opportunity to see it clearly had already begun to diminish. Each day after, the object became fainter, farther away, harder to measure. What humans captured remained valuable, but far less than what might have been obtained if it had been detected earlier. After Oumuamua, the question shifted. How can we recognize interstellar objects while they are still close enough bright enough, and with enough time for multiple telescopes to track them. 2 years later, the sky provided another example. 2I Borisov was discovered in 2019 and confirmed as an interstellar comet. Borisov differed from Oumuamua in key ways. It exhibited clear cometary activity, with gas and dust easily observed, and was detected before perihelion, giving astronomers more time for measurements. Its appearance helped balance the picture. Interstellar objects need not all resemble Oumuamua. One may be quiet, low in dust, and difficult to classify. Another may reveal its cometary nature more clearly. Even these two examples already illustrate emerging diversity. Oumuamua no longer represents all interstellar objects. It was the first recognized, but not the sole archetype. Borisov shows that an object from beyond the solar system can carry gas and dust like a familiar comet. Oumuamua shows that another object can pass almost barren, lacking a clear tail, yet still leave subtle traces in light and motion. This variation brings the question down to reality. Interstellar objects do not come in only one type. They can vary widely. As the list of such objects grows, Oumuamua retains its special position. The first remains the one that opened the door, but each new visitor reduces the pressure on a single case. One object is insufficient to understand an entire population. 2 objects are only the beginning. More will reveal what is common, what is rare, what belongs to Oumuamua's unique history, and what may be shared characteristics of fragments ejected from parent star systems. Sky survey work thus becomes even more important. A telescope must not only see deeply, but also widely and repeatedly. Interstellar objects may move quickly. They do not wait for observation schedules. They do not return periodically to allow humans to correct mistakes. If discovered late, the best data may already have passed. If processed slowly, precious observing nights may be lost. Without retrieval of older images, trajectories are shorter, errors larger, and the object's origin harder to infer. A new faint point in data is not enough to say much, but if it can be found in previous images, the story gains history. Its prior positions extend the observation arc. A longer arc yields a more reliable orbit. A secure orbit distinguishes solar system objects from a fleeting interstellar visitor. For Oumuamua, every measurement mattered because it faded so quickly. In future cases, if detected earlier and traced through better archival data, humans can preserve more of the trajectory before the object moves away. Such discoveries also require coordination. One telescope may spot the object, another may measure color, a third may search for gas or dust signals. More powerful instruments can track brightness variations to infer shape and rotation period. Each type of observation captures only part of the object, and the time available for all is very short. For interstellar visitors, astronomy is not just about looking up. It is about responding swiftly to a target that is already departing. Oumuamua also makes the idea of sending a probe to an interstellar object more tangible. It is not easy. Such objects move fast, are discovered late, and rarely lie on convenient trajectories for intercept. With Oumuamua, the opportunity had nearly passed by the time humans realized its significance. But that missed chance leaves a clear problem for the future. If detected earlier, with preparation and a suitable orbit, could a spacecraft fly past an interstellar visitor? The question remains difficult, yet it is no longer mere speculation. It belongs to launch speed, orbital mechanics, warning time, and readiness. Even without a spacecraft, remote observations can provide abundant information if done at the right moment. An object with clear cometary activity can reveal gas and dust in its spectrum. An object lacking a visible tail can still show shape through brightness variations. An object with a reddish hue may suggest a surface long exposed to radiation. With more cases, astronomers can begin comparison. Which objects resemble comets more? Which are drier? Which exhibit non-gravitational acceleration? Which have unusual colors? Such comparisons will make Oumuamua less solitary in the data. The first often does not tell the full story. Oumuamua opened the door, but it did not remain long enough to answer everything. Borisov arrived later, showing a different face of interstellar objects. Future visitors may be even more diverse. Some may contain abundant ice, some may be nearly dry, some may have clear tails, some may be faint points like Oumuamua. The more examples, the less the interstellar question depends on a single story, and the field begins to have real comparative samples. The sky did not become more frightening after Oumuamua, it simply became more open. The solar system still has its order, with planets, moons, asteroids, and comets belonging to the sun's gravitational realm. But that order does not exist inside a sealed box. From time to time, an object from elsewhere can pass through. It does not need to collide, stay, or carry a message. The act of passing through and being measured is already enough to show that the solar system is part of a larger galactic environment. Interstellar fragments do not need a purpose to become important. They are not sent as intentional messengers. They are not seeking Earth. They simply move under gravity and inertia, carrying traces of where they once formed and of the journey after they were ejected. If one of them passes close enough to the sun, the light of our star can make it appear in a telescope. At that moment, an unnamed piece of matter from very far away becomes a rare opportunity to look indirectly into other planetary systems. A few objects cannot tell the story of the entire galaxy. Oumuamua and Borisov are only the first points in a still very short list. They are not enough to tell us what size interstellar objects usually are, whether they usually contain more ice or more rock, what colors they tend to have, or how strongly they usually become active when passing near the sunday. But every statistic begins with its first points. Each new visitor will make these questions a little less vague. Each new trajectory, each new spectrum of light, each new sign of gas or dust will help humans better understand the material thrown out of star systems. Oumuamua left without returning, but the way we observe the sky after it has changed, survey systems will need to pay closer attention to fast-moving objects with unusual orbits. Old data archives will be checked more carefully when a new point of light is discovered. Coordinated observations will become more important because each visitor's time is brief. Ideas for missions that could fly past an interstellar object will be considered more seriously. A faint point of light was enough to show that humans can encounter material from another star system within our own observational reach, if we know how to look at the right moment. The first visitor did not give us much time, but it gave us a direction for looking. Most of the small points of light in the data will still be familiar solar system objects, but from time to time, very rarely, one of them may not have been born here. It may have traveled through the darkness between the stars for a very long time, entered the sun's light, appeared in a few images, and left before humans could fully understand it. Recognizing that sooner, preserving more data, and preparing better for the next encounter is the task that Oumuamua has left for astronomy. The clearest mark that Oumuamua left is not only in the numbers of its orbit or the debates about its shape. That mark also lies in a very practical lesson. If an interstellar object is recognized too late, most of its story may have already passed. The first visitor had already passed near the sun before it truly caught human attention. By the time telescopes turned toward it more frequently, the object was fading day by day in images, carrying details beyond measurement. Therefore, what future visitors need most is not louder explanations, but an earlier encounter. An interstellar object does not give humans much time. It does not orbit the sun to return seasonally, nor does it remain in a familiar region for astronomers to observe again the next year. It enters, the sun bends its path, then it leaves the system. If detected while still approaching, the data could be far richer. Its brightness could be tracked over many stages. Its color could be measured while the signal is still strong. Its orbit could be determined more precisely. If gas or dust is escaping, Telescopes have additional opportunities to detect it before the object becomes too distant and faint. This lesson makes wide-field sky surveys more important. A telescope looking deeply into a small region can see very distant galaxies, but interstellar objects require a different kind of vigilance. They can appear in any region of the sky as a small point of light among countless others, moving quickly across the background stars. To recognize it, the sky must be imaged repeatedly, compared continuously, and processed quickly enough so that an unusual motion is not lost in the vast data stream. Oumuamua showed that a major discovery sometimes begins very small, so small that only a consistently operating observation system could capture it. Next-generation survey telescopes are built for this pace of work. They do not just image the sky to make beautiful pictures, they create continuous records of what changes. A distant star appears nearly stationary in the images. An asteroid moves slightly. A comet may brighten or show a faint coma. An interstellar object, if it appears, may move along a path that quickly diverges from the familiar objects of the solar system. The challenge is not just capturing faint light, but also rapidly understanding which motion that light belongs to. The Vera C. Rubin Observatory is a prime example of this approach. With its ability to survey the wide sky over many years, systems like Rubin can increase the chances of detecting small, faint, and fast-moving objects, including interstellar visitors. Its strength lies not only in a large mirror, but in its wide, repeated coverage, recording changes and linking points of motion before the object fades. If a point of light appears in multiple consecutive images, its trajectory begins to emerge. If that trajectory does not close around the sun, the question of interstellar origin can be raised much earlier than in 2017. Early detection also depends on how motion is processed in images. A fast-moving object can be stretched into a short streak during exposure, making it harder to recognize than a round point of light. It may also change position quickly between exposures, complicating the task of linking points to the same object. For familiar asteroids and comets, survey systems already have experience, but an interstellar object can arrive at higher speed, an unusual direction, and an orbit that does not match common assumptions. Software, algorithms, and data scanning are therefore as important as the telescope itself. Once an interstellar candidate is identified, other observations must begin almost immediately. One observatory may detect it, but multiple instruments are needed to understand it. A large telescope can measure brightness more accurately. Spectroscopy can search for gas. Infrared observations can reveal additional information about temperature and surface. Continuous imaging can track brightness changes, helping infer rotation and possible shape. If dust or a gas coma is present, it must be sought while the object is still bright. If absent, that absence must still be recorded sensitively. Each measurement is a small opportunity, and that opportunity decreases with distance. Old data also plays a crucial role in regaining time. An object reported today may have already appeared in images from days or weeks earlier, just unnoticed. Retrieving these past appearances extends the observation arc. A longer arc allows a more precise orbit. Speed can be better determined. Direction before discovery becomes clearer. With Oumuamua, every measurement was precious because it was detected while already receding. For future visitors, revisiting archived data could turn a late discovery into a longer story, even though the object will not wait for humans. An earlier encounter also makes hypotheses more robust. If a Oumuamua-like object has a small non-gravitational acceleration, but is observed over a longer period, astronomers can see how that acceleration changes as it moves away from the sunday. If gas escapes, they can check at what distances, how strong, and whether dust is carried. If no gas is seen, limits can be established more confidently. If brightness varies strongly, a longer observation series helps make shape models less ambiguous. More data does not guarantee all questions are solved, but it reduces reliance on gaps. The idea of sending a spacecraft to an interstellar object also becomes clearer when the story is viewed in time. A target like Oumuamua moves fast and does not return, so if detected after passing, intercepting it is nearly impossible. But an object detected earlier could give humans additional months, even more, to calculate a trajectory and see if a flyby mission is feasible. This is still very difficult, requiring high launch speeds, prior planning, and a favorable trajectory. Still, Oumuamua transformed that question from distant imagination into a technical challenge that can be considered seriously. A flyby of an interstellar object would change many things. Shape would no longer have to be inferred, mainly from brightness. The surface could be seen directly. If there were dust layers, impact craters, cracks, bright and dark regions, or signs of activity, they could be recorded in images. If gas were escaping, instruments could measure its composition from much closer range. Even a mission that did not return a sample would provide far more data than a faint point of light in a survey image. Questions that once clung to Oumuamua because of limited data could be answered more clearly with a future target discovered at the right time. While waiting for that possibility, telescopes remain the main tool. Each new visitor will help test the questions left behind by Oumuamua. If many interstellar objects have clear tails, Borisov may represent a more common group. If many resemble Oumuamua low in dust, reddish, hard to classify, and showing unusual acceleration, then the first visitor will no longer seem so isolated as an exception. If every object is different, that will show that fragments ejected from parent star systems may be highly diverse, reflecting many birthplaces, many compositions, and many histories across the galaxy. Early detection helps prevent a first case from carrying too much meaning. Oumuamua may be special, but it may also look special because humans observed it under unfavorable conditions. It was discovered late, with limited data, no close-up images, and no sample. Another object found earlier may show that features once considered mysterious actually have simpler explanations, or, conversely, may clarify that Oumuamua truly belongs to a rare class of object. The answer will not come from further speculation about a visitor that has already departed, but from meeting more visitors with better data. Wide-field sky surveys can help that list grow. The discovery rate will depend on many factors: how abundant interstellar objects really are, how large they are, how well their surfaces reflect light, how close they pass to the sun, and whether observing systems can process fast motion in time. With so little data, not every number can be predicted in advance, but the direction is clear. Looking wider, repeating observations more often, and processing faster will increase the chance of encountering such objects. Oumuamua therefore remains at the center of this story, even though it has moved far away. It is not only the first strange object to be found, it points to what needs to improve: earlier detection, more measurements, faster coordination, better recovery of old data, and preparation for the possibility of a target favorable enough for a flyby. A faint point of light in 2017 helped astronomy see the concrete requirements of a new field more clearly. There is no need to exaggerate it into something larger than the data. Its limited data alone was enough to show where the next encounter must be handled better. The next visitor may not resemble Oumuamua. It may be brighter, darker, have a clearer tail, or appear almost bare. It may be discovered while still far from the sun, with enough time for many observatories to follow it. Or it may appear in a short window and vanish quickly, like the first visitor. But if humans recognize it earlier, the story will begin from a different point. No longer only reconstructing the final part of the journey, no longer trying to infer too much from a few thin traces. Next time, perhaps we will see an interstellar visitor while it is still entering the light, before the most important data have slipped away. Oumuamua showed the cost of arriving late. Future telescopes may return to humans some of that lost time, not by slowing the object down, but by recognizing it faster. In the science of interstellar objects, time is data. One extra night of observation can make the orbit more certain. One additional color measurement can make the surface clearer. A better spectrum can reveal whether gas is present. A longer brightness sequence can make the shape less ambiguous. The object will still leave, but its story may remain with us more fully. Future encounters may be less blurry, not because interstellar visitors will be less strange, but because humans will know how to preserve more of what they reveal. Oumuamua arrived as a first test, with too little time and too many questions. Later objects may arrive in a better era of observation, when data are processed more quickly, telescopes see wider regions of the sky, and astronomers have experience with paths that do not return. If that happens, the first visitor will still keep its role as the one that opened the way. It showed how quickly we must look when a point of light that does not belong here begins to cross our sky. The closer we come to the end of Oumuamua's journey, the remaining feeling is not that we have fully grasped it more clearly. On the contrary, the more layers of data are placed beside one another, the more this visitor reveals a very ordinary truth that is still difficult to accept. Some phenomena in the universe pass by too quickly, too far away, and too faintly for humans to understand completely in the first encounter. Not because science is powerless, and not because the object lies beyond nature, but because the meeting was too brief and the data too limited. A small object passed through the sun's light, left behind a few real signs, and then moved away before the largest questions had enough time to be answered. The humility in this story begins with its size. Oumuamua is not a planet, not a large moon, not a brilliant comet that could be followed by many telescopes for a long time. It is a small, dark, difficult object to observe. When it was discovered, it had already passed the most favorable part of its path near the sun and was fading day by day. What humans could measure had to come from a very small amount of light reflected from its surface, from changing positions across images, from rising and falling brightness, and from a path reconstructed through careful calculations. An object this small does not need to hide itself in order to become difficult to understand. The observing conditions alone made every piece of information about it thin. Science is often imagined as a journey from question to answer. But with Oumuamua, that journey is more like moving from one large question to clearer questions. At first, the question was what this object was. Once its path was understood, the question became why it came from beyond the solar system. When its light changed, the question shifted toward its shape. When its color was measured, the question opened toward what kind of environment its surface had experienced. When no clear tail appeared, the comet question became more difficult. When the slight acceleration emerged, the question of an additional force opened again. Each partial answer did not close the story, it made the next question more precise. That is not a failure. It is often how science works when it meets a rare phenomenon. A first observation is rarely enough to build a complete picture. It only confirms that the thing worth studying truly exists. Oumuamua did that. It showed that interstellar objects are not only things that may exist in models, but things that have passed through our region and been recognized. It also showed that interstellar objects may be harder than expected, discovered late, fading quickly, carrying signs that do not fit neatly into familiar categories. Instead of giving us a complete file, it placed a real case on the table, specific enough to study and incomplete enough to remind humans that better observations are needed. That incompleteness appears in many places. There is no close-up image, so its true shape remains uncertain. There is no sample, so its inner composition can only be inferred. There were no long observations before it came close to the sun, so any activity it may have had was not followed fully. No escaping gas was directly measured, so models involving hydrogen or other forms of outgassing still rely on indirect signs. Its home is unknown, so its history before passing through the solar system remains beyond view. These missing pieces do not erase the data we do have, but they set clear boundaries for every version of the story. Keeping those boundaries matters. If exaggerated, Oumuamua can easily become a symbol larger than the data allow. If minimized too much, it becomes only a strange point of light and is forgotten. The right view lies between those two extremes. It is a real interstellar object. It truly has remarkable features. It has reasonable natural models that can explain many of its signs. At the same time, it is still not fully understood. A mature scientific story does not need to choose between wonder and accuracy. It can hold both, as long as each is placed where it belongs. Oumuamua also humbles humans before time. Its journey before reaching the solar system may be longer than any civilization on Earth. It may have drifted through the darkness between stars for millions of years or more. While we saw it only during a very short interval, that difference is enormous. An object with such a long history left humans only a few weeks or months of useful data. Most of its life happened where no one was watching, with no telescope accompanying it, with no record preserved. We only caught the final segment of a very long journey through our region. The humility also lies in the fact that the solar system is not the center of the story. For humans, Oumuamua passing near the sun was a special event, because that was when we could see it. But for the object itself, the region near the sun was probably only a brief section of a much longer path. It did not come because of Earth. It did not pass by in order to be discovered. It did not leave for any purpose. It simply moved according to inertia and gravity. While human recognition was the result of a coincidence between trajectory, timing, and observing ability, that does not make the discovery less important. It only reminds us that our view is always tied to our very small position in the universe. A small object like Oumuamua also shows how deeply astronomy depends on light. Humans did not touch it, did not hear it, did not see it as a body with a clear surface. Everything began with reflected light. That light was too weak to form a detailed image, but strong enough to record brightness, color, and position. From there, astronomers built its orbit, inferred its shape, looked for surface clues, and tested its motion. The entire story is built from a very small amount of information taken from an object already moving away. This makes what science accomplished more impressive, but it also makes its limits more visible. Not every limit needs to be erased immediately. Some limits tell us what must be prepared for next time. Oumuamua gave us no close-up image, so flyby missions to interstellar objects become more worth considering. It gave us no early data, so sky surveys need to detect faster. It did not give enough information about escaping gas, so spectroscopic and infrared observations must be mobilized sooner for future visitors. It did not provide a population for comparison, so objects like Borisov and future discoveries become important. Each unknown is not only an empty space, it is a guide for how to observe next. Perhaps a future interstellar object will be easier to understand. It may be discovered while still approaching, bright enough to follow for longer with a clearer tail, or passing on a more favorable trajectory. Or perhaps the next object will be even more difficult, smaller, fainter, less active. There is no guarantee that nature will choose a convenient case for humans. But after Oumuamua, that inconvenience is no longer entirely surprising. We now know that an interstellar visitor can come and go very quickly. We know we must look wider, process faster, and keep hypotheses within the limits of the data more carefully. Another lesson lies in how we handle the unknown. When data are scarce, bold explanations can become attractive. An unusual shape, a small acceleration, and a missing tail can carry imagination very far. But Oumuamua shows that fascination does not need to leave nature behind. A model involving old ice, hydrogen, radiation, and the warmth of the sun can be deep enough to make the story memorable. An object ejected from its parent star system, drifting through the interstellar environment, reddened on its surface, and then reacting gently when it meets the sun is already a very large story. We do not need to add too much to the unknown for it to become wondrous. This humility does not make the universe smaller. It makes the universe clearer. An uncertain answer is not emptiness. It is part of the process of understanding. A model that is not fully confirmed is not meaningless. It is a way for humans to try connecting pieces of data through mechanisms that can be tested. An unresolved mystery does not need to become a legend. It can remain a real question, waiting for better observations. With Oumuamua, the truth likely lies somewhere among ordinary physical processes occurring under unusual circumstances. A small object, a long journey, a brief encounter, and a very limited amount of data. Looking back at the entire set of traces, Oumuamua feels like a test of patience. It does not reward quick conclusions. It does not give a beautiful image for everyone to look at and agree upon. It forces scientists to work with uncertainty, observational limits, unconfirmed models, and competing possibilities. It forces the storyteller to be careful, because with only a little overstatement, the object becomes something other than itself. An interstellar visitor does not need to become a symbol of every mystery in the universe. It is already important enough as the first object to show that a piece of matter from between the stars can pass through our region. Its smallness is exactly what makes the discovery memorable in its own way. A large planet can draw attention through scale. A distant galaxy can impress through the number of stars it holds. A black hole can overwhelm us with gravity. Oumuamua is different. It is small, faint, data poor, image poor, and still without a final answer. Yet it opened the solar system in human understanding. It showed that beyond the familiar objects, there are paths crossing through, fragments of matter that do not belong here, brief encounters that humans would miss entirely if we were not watching at the right moment. Somewhere out there, between the stars, countless other small objects are likely drifting along similar paths. Most never come close enough to the Sunday. Some may pass through, but remain too faint to see. Some might appear in the data only to be overlooked. Oumuamua was a case that humans managed to recognize, even if not fully understand. That makes it both ordinary and exceptional. Ordinary because it could be one of many fragments ejected from stellar systems. Exceptional because it was the first fragment confirmed by humans passing through our region. At the end of its observational journey, this visitor left no complete answer, but it left a more careful perspective. Science does not need to conquer a mystery by closing it prematurely. Sometimes the triumph lies in discerning what is truly known, what is only a model, and what must await further discovery. With Oumuamua, that boundary is crucial. It prevents the story from sliding into either of two extremes, overstating or understating. It keeps the object in its proper place, a real discovery, a highly plausible natural object, a case with many remaining questions, and a first milestone in studying interstellar visitors. What Oumuamua took from human sight may have exceeded what it left behind, yet what it did leave is enough to reshape how humans prepare for the sky. It highlights the necessity of wide surveys, rapid response, archived data, flexible models, and careful storytelling. It reminds us that even a small object can expose a system of big questions, so long as humans pay close attention to subtle signs. It is a humble lesson, yet not a small one. The visitor has now passed beyond our region of sunlight, with no reason to return. It will continue into the wider space, drifting farther from the sun, farther from the telescopes that once observed it. But the mark it left in science does not depart in the same way. Its trajectory remains in the data. Models about it are still discussed. Future objects will be compared against it. And each time a new faint point with a strange orbit appears in survey images, the shadow of Oumuamua returns as a very practical reminder. Some things visit only once, and to understand them, humans must learn to look faster, more clearly, but also with greater humility before what cannot yet be known. Some questions do not close when a celestial object leaves our sight. With Oumuamua, It is precisely what remains unknown that makes it linger longer in scientific memory. Its trajectory was recorded, brightness measured, color analyzed, natural models proposed, but most of its history stayed out of reach. It did not return for a second observation. There is no subsequent season to await its reappearance. No long orbit around the sun allowed telescopes better preparation. It passed once, close enough to be noticed, then continued on a path not belonging to the solar system. When an object departs like this, what remains is not a complete sense of loss. The data remain. The measurements remain. The questions take clearer shape. Yet behind all of it lies a quieter shift. The solar system is no longer imagined as a completely closed environment. The sun is still the center of familiar planets. Earth still follows its orbit. Jupiter, Saturn, asteroids, and comets remain part of our star's long story. But within that picture, Oumuamua left a thin slice, a sign that sometimes material from another star system can pass through this region, neither staying nor returning, merely gliding by and disappearing. Before humans recognized it, that path had existed for a long time. Planetary systems can still eject material. Fragments of rock and ice can leave where they formed. Interstellar space still contains dust, thin gas, radiation, and small objects drifting in silence. Oumuamua did not create that reality. It only made it pass close enough for humans to measure. A possibility became a point of light in a survey image. A potential gained coordinates, velocity, brightness, color, and a name. Thus, the significance of Oumuamua does not lie in becoming extraordinary in a loud sense. Even if it were merely a fragment of natural material ejected from a distant star system, the story is already profound. A small piece that once belonged elsewhere, drifting through interstellar darkness, its surface aged by radiation, passing near the sun for just a short segment of its journey, is rare enough from a human perspective. Its strangeness requires no embellishment. It exists in the fact that a non-native object can be revealed by the sun's light. One can imagine it as a fragment carrying the history of a place whose name we do not know. Not history written in letters, but through trajectory, color, surface, and subtle reactions when passing near another star. If its exterior is dark red from long-term radiation, that color is part of its journey. If brightness varies due to irregular shape, the pattern is how its distant form subtly exposes itself. If a tiny thrust comes from a barely detectable outgassing, its motion records a final response between old ice and the sun's warmth. All of this requires no grand explanation. These natural details, placed correctly, are enough to make the visitor memorable. Oumuamua also reveals human smallness in a way that is not burdensome. We are intelligent enough to build telescopes on high mountains, patient enough to compare faint points over many nights, precise enough to recognize a non-closed orbit around the Sunday. Yet at the same time, we arrived late. We do not know its true shape. We do not know its home. We do not know exactly how long it drifted before passing by. Strength and limitation stand side by side in the same discovery, and that coexistence makes the story authentic. Science does not shrink by acknowledging what it does not yet know. It becomes more reliable by not rushing to fill every gap with too quick answers. An object like Oumuamua teaches humans to watch the sky with a different attention, not only to what is brightly shining, not only to grand images, beautiful planets, radiant nebulae, distant explosions. Sometimes, something important appears as a very faint point, drifting through a short observational window, and without consistent survey systems, it could pass by unnamed. After Oumuamua, faint points in the data carry a new possibility. Most still belong to the solar system, but very rarely. One of them could be material from elsewhere, passing by before returning to darkness. The sky does not become more alien. It becomes broader in understanding. The solar system remains our home, but that home is not isolated from the flow of the galaxy. It is not walled off from the rest. Planets still orbit the sun, But beyond those familiar paths exist open trajectories, transient visitors, small fragments, not native to this system but capable of passing through its light. A brief flyby adds a new depth to the familiar picture. We live in a star system with doors open to the galaxy, though those doors are usually too dark for the human eye to perceive. Perhaps it is precisely Oumuamua's non-residence that clarifies this feeling. If it had been captured by the sun, if it became a new comet orbiting our system, it would have joined the list of objects that can wait. But it does not belong to that kind. It passed and continued onward. That departure confirms its nature. A true visitor, with no residence in an orbit around the Sunday. It is like a line bent momentarily by gravity, then opening again toward the distance. Within that brief curve, humans see evidence that interstellar space is not merely distance, but a realm where matter moves. Subsequent discoveries like 2I, Borisov, and later recorded interstellar objects make that door feel less lonely. Oumuamua is not the whole story. It is the first recognized sign. Other visitors may carry dust, gas, more obvious comet tails, or remain as discreet as it. Each new case will help humans understand the diversity of interstellar objects. But no matter how long the list grows, the first visitor holds a distinct place, not because it is the most comprehensible, but because it compelled humans to realize such objects truly can pass through our sky. That fact need not be told in a loud voice. A fragment from another star system passing by is not everyday news, but it is not something frightening either. It does not displace planets from their orbits. It does not pose a hazard in this story. It quietly shows what occurs on a scale of time and space far beyond our daily life. Planetary systems form. Some fragments are ejected. Those fragments drift through the galaxy. Very rarely, one passes through the light of another star and is observed. On that scale, coincidence matters. Oumuamua was not seeking Earth, and Earth was not waiting for it. Yet its path, the sun's position, the capability of pan-stars, and the timing of the surveys met just right. If any of these had shifted, it might not have been detected. It would still have passed, but humans would not have known. Recognition sometimes depends on such fragile factors. A point of light at the right moment, a sufficiently sensitive algorithm, a person checking data, a rapid orbit calculation. From those very practical steps, a new door in understanding opens. For that reason, future telescopes are not only better machines, they are one way humans learn from having arrived late. If the next interstellar object is discovered earlier, the story may be more complete. Its shape may become clearer. Gas and dust, if present, may be searched for more carefully. Any unusual acceleration, if it appears, may be followed for longer. One day, a spacecraft may fly past such a visitor and turn a faint point of light into an object with a real surface in photographs. Those possibilities do not make Oumuamua less important. They show that it did the work of the one that came before, leaving behind a lesson for future encounters. But even if nothing more is ever known about Oumuamua itself, it has already changed part of the story. The solar system is no longer told only from the inside. It can also be told through objects passing through it. A piece of matter from elsewhere reflected the sun's light, appeared in Earth's data, and disappeared. That moment connected three scales: a small object, a familiar star system, and the vast galaxy where fragments of matter can wander for ages before meeting the light of another star. No brilliant image is needed. That connection alone is enough to make the picture wider. What remains in the end is not a definitive answer about Oumuamua. It is a more accurate feeling for where we are. Earth does not stand alone beneath a sealed sky. The sun does not hold all matter around it behind an uncrossable boundary. The galaxy is not made only of stars separated by darkness, but also of small fragments moving through that darkness. They may rarely be seen. Most may never be named. But the existence of one confirmed visitor shows that the sky is wider, not only because of distance, but because of paths that connect distant places through the motion of matter. Oumuamua continues moving away, unaware that it has become a milestone in the understanding of a small species on a small planet. It will leave the region where telescopes can follow it and sink deeper into interstellar space. Ahead of it may be millions of years more, perhaps another passage near some distant star, or perhaps a very long journey with no significant encounter at all. Humans will not be able to follow that road, but the part of its path that passed near us remains preserved in data, and that data is enough to remind us that an object does not need to stay long to open a new way of seeing. If this journey must settle into one feeling, that feeling is openness. Not the loud openness of a newly announced secret, but the quiet openness that comes when a familiar boundary becomes a little less rigid. The solar system is still home, but that home has visitors passing through. The sky is still calm, but within that calm, there is motion. The darkness between the stars is still immense, but within that darkness, there is not only emptiness, but small, cold, silent fragments of matter carrying the histories of distant places. Oumuamua did not speak to us through a signal. It left no message. It confirmed no single hypothesis completely. It simply passed through. But that passing was enough. An open trajectory, a faint point of light, a small object that did not return all of it, added another doorway to the familiar picture of the solar system. From now on, whenever we think about the region around the sun, we can remember that beyond the stable orbits and familiar bodies, there are other roads as well, very long and very dark, where matter from distant star systems may occasionally pass through our light. The first recognized visitor has departed. Others may be somewhere out there, not yet close enough, not yet bright enough, not yet within our view. One day, perhaps another faint point will appear in the data, and this time humans will recognize it sooner. Telescopes will turn toward it. Measurements will begin. Old questions will return with new data. And when that happens, Oumuamua will remain behind as the first marker, reminding us that between star systems there is not only distance, but real flybys, brief, true, and deep enough to make the sky wider in human understanding.